Hello everyone and welcome back. Today we are going to dive into a classic topic that still confuses many newcomers and even some experienced developers. What's the real difference between C and C++? And more importantly, why does it matter? Let's get started. When people talk about C and C++, it often comes with the question, aren't they basically the same? Or C++ is just C with classes, right? That's partially true, but also very incomplete. C and C++ share a lot of syntax, and yes, C++ was originally built as an extension of C. But the philosophical, structural, and practical differences between the two are huge. To understand this, let's start with the basics. C is a procedural programming language. That means it's all about functions, control structures, and linear sequences of instructions. Code is organized into functions and data structures, but there is no concept of classes or objects. C++, on the other hand, is a multi-paradigm language, but primarily object-oriented. It supports procedural programming like C, but it also adds classes, inheritance, polymorphism, and encapsulation, the pillars of object-oriented programming. So what does this actually mean? Well, here is a tiny example. In C, you might write this. In C++, you could encapsulate this into a class. Same functionality, but the C++ version combines data and behavior. That's encapsulation. In C, data and functions are separate. In C++, they live together, which is a huge deal for organizing large codebases. Another key difference is how the two languages approach abstraction. C gives you full control. You manage memory manually with malloc and free. You can do pointer arithmetic, and you can manipulate raw memory. This makes C very powerful but also very risky. There is no safety net. You can easily have buffer overflows, memory leaks, dangling pointers, and no compiler warning will save you. C++, in contrast, offers an abstraction mechanism that helps prevent these problems, if used correctly. You get constructors and destructors, smart pointers, RAII, and the standard template library. Instead of writing manual memory management code, in C++ you can often do something like this. There is no manual memory allocation, no manual cleanup. The std vector handles everything internally. This improves code safety, readability, and reduces bugs, but it also comes at the cost of a slightly steeper learning curve and potential overhead if you don't understand what's going on under the hood. C is minimal. The standard library is small and the language has a limited number of features. This makes it lean and fast, especially in embedded systems, microcontrollers, or operating systems where every byte counts. C++ is a much larger language. It supports templates, exceptions, multiple inheritance, function overloading, operator overloading, and much more. This richness allows developers to write complex systems more quickly and with better structure, but it also means you can shoot yourself in the foot in a very complex way if you misuse these features, so there is a trade-off. Minimal and bare bones versus powerful and feature-rich. C uses macros to achieve generic behavior, but macros are dumb. They are handled by the preprocessor and don't respect scope, types, or errors. Here is an example. Looks simple, but this can cause bugs if A or B have side effects. C++, in contrast, uses templates, which are type-safe and part of the language itself. The compiler type checks this. It behaves like a real function. This allows for powerful generic programming, which is the basis of the STL. This one is massive. The C standard library gives you basic input-output, string manipulation, memory functions, and that's about it. In C++ you get the STL, a whole bunch of data structures and algorithms. Need a hash map? Use std unordered map. Need a dynamic array? Use std vector, and they all come with iterators, algorithms, and memory management built in. This doesn't just save time, it standardizes code and improves reliability. C doesn't have built-in exception handling. You use return codes and manually check for errors. In C++ you can throw exceptions. then catch them. This leads to cleaner error handling and separation of concerns. But again, it adds complexity. Another important difference is how the languages handle compilation. In C, the compilation model is simpler. Every C file is compiled into an object file, and then they are linked together. The function definitions must exist at link time, or you get errors. C++ adds templates, inline functions, function overloading, and those complicate the compilation process. Templates, for example, are instantiated at compile time. This can lead to longer build times and larger binaries, especially if used heavily. So if you're building large systems, managing compilation in C++ can become a serious task, especially without tools like CMake or build systems like Bazel. So where is each language used? C is still dominant in low-level systems, operating systems, embedded firmware, device drivers, and kernels. Why? Because of its low overhead, speed, and fine-grained control. C++, on the other hand, is used in applications where performance and structure are needed. Game development, financial systems, simulation games, browsers like Chrome, these are often built in C++. In fact, most AAA games are written in C++ for a reason. You get the power of C with higher level abstractions, which are crucial for managing large code bases. Now here is a tricky question. Can C and C++ work together? Yes, mostly. C++ is in a way a superset of C. Most C code can be compiled as C++ with minimal changes, but not all of it. There are subtle incompatibilities. For example, implicit void pointer conversions that work in C but not in C++. To call C code from C++, you typically wrap it like this. This tells the compiler not to mangle names so it can link properly with C code. But calling C++ from C, that's harder, because C doesn't understand classes, exceptions, or templates. So if you need two-way compatibility, you have to be careful. This is the most subtle, but perhaps the most important difference. C was designed by Dennis Ritchie to be close to the machine, simple and portable. It gives you just enough abstraction to be productive without getting in the way of performance. C++ was designed to scale, to manage complexity in large software systems. It's about abstraction, reuse, and flexibility. That's why C++ keeps adding features. Lambdas, const-expr, modules, concepts. It's evolving to support modern development needs. C, on the other hand, has remained more or less the same over the decades. So the question is, do you want full control or structured abstraction? That's what it boils down to. Alright, so why does any of this matter? It matters because when you choose a language for a project, you are not just choosing a syntax. You are choosing a philosophy, a toolchain, a runtime model, and a trade-off. If you are building firmware for a washing machine, use C. If you are writing a physics engine for a 3D game, use C++. If you want fine control over performance and memory, C might be better. If you want scalability, templates, and safety, C++ shines. And as a developer, even if you specialize in one, it's critical to understand both. Many real-world projects combine the two. To wrap it up, C is fast, reliable, and dangerous. C++ is powerful, flexible, but harder to master. Neither is better than the other. They serve different purposes, and the best programmers know when and how to use each one. So the next time someone says C++ is just C with classes, you will know how to answer. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one. Hey everyone, welcome back. Today we're talking about something that lives deep under the surface of your code, but can have a real impact. The difference between big endian and little endian byte ordering, and why it matters in C++ programming. Let's start with a simple question. What does endian even mean? In computing, endianness refers to the order in which bytes are arranged in memory when storing a multi-byte data type, like an int, float, or double. Let's take a 32-bit integer as an example. This value takes up 4 bytes in memory. Now, depending on the system architecture, those 4 bytes can be stored in one of two ways. Big endian, which means most significant byte first, and little endian, which means least significant byte first. In big endian, memory will look like this. But in little endian, memory will look like this. Same integer, different byte order. So which is more common? Most modern systems, including 32 and 64-bit architectures, basically all consumer desktops and laptops, use little endian. But that's not universal. Some network protocols, embedded systems, and legacy hardware still use big endian. Which means if you're writing C++ code that talks to other systems, writes binary files, or works with low-level memory, endianness matters. How can you see this in C++? You can actually inspect memory layout using a little code. If you run this on a little endian machine, you will see this. That's the least significant byte first, little endian. On a big endian system, you would see this. Why does endianness even matter? It might seem like a low-level technical detail, but there are a few situations where getting this wrong can completely break your program. Let's go through the main ones. If your program writes raw binary data to a file and that file is read by another system, you have to agree on a byte order. Let's say your C++ program writes integers directly. Now, someone on a big endian machine tries to read that file. They are going to interpret the bytes differently unless they know the format. This is why most binary file formats, like PNG and others, define a fixed endianness, often big endian. It ensures consistency across platforms. Another big one is networking. The internet uses network byte order, which is big endian. So if you are sending data over a socket and your machine is little endian, you have to convert. That's where functions like these can come in. Without this conversion, two computers might completely misinterpret the data they are exchanging. If you are writing a custom serialization system, maybe for a game engine or distributed app, you will need to define an endianness and stick with it. Otherwise, one client might send little endian and another might receive big endian. Suddenly, all your positions, scores, or timestamps are scrambled. In embedded systems, you don't always get to choose your architecture. Some chips are big endian, others are little. Some can switch. So, if you're writing portable code, like a library that might run on different chips, you need to account for endianness. Same goes for firmware updates, low-level drivers, or cross-compilation scenarios. Ignoring endianness can lead to silent bugs that only appear on specific hardware. There is no standard C++ macro for this, but you can detect it like this. It works by checking whether the least significant byte is stored first in memory. If you are using C++20 or later, there is a cleaner way with the bit header. That's the modern standard way. To convert values between big endian and little endian manually, you will need to swap the byte order. Here is a simple function for a 32-bit integer. This rearranges the byte explicitly. There are also compiler intrinsics and built-in functions for this. Be careful when writing structs directly to disk or over the network. If you just dump this struct into a binary file, you're not just risking endian issues, but also alignment, padding, and compiler-specific layout. The best practice is to write each field individually, in a known order and format, and convert the endianness manually if needed. Does changing endianness hurt performance? Not much. Modern CPUs can swap bytes very fast. But it's still a good idea to minimize conversion and only do them at boundaries, like file input-output or network transmission. Inside your application, you can keep everything in native format for speed, and only convert when importing or exporting data. So which one is better? That's a bit like asking, is driving on the left or right better? Both big endian and little endian have their merits. Big endian is more intuitive to read. Most significant byte comes first, just like with right numbers. Little endian is easier for incrementing and certain bitwise operations. But in the end, it's not about which is better. It's about being aware and consistent. Let's wrap up with a few practical tips. First, know your platform. Check your system's endianness if you are doing low-level work. Second, never assume endianness in portable code. Always detect or define it. Third, when saving binary files or sending data over the network, pick a standard endianness, usually big endian, and stick to it. If you are dealing with byte buffers, write functions that handle endianness for you. If you can, test your code on both little and big endian systems, or at least simulate them. Endianness is one of those things that seems unimportant until it breaks something. It's not something you think about every day, but if you care about portability, networking, performance, or just writing robust, low-level code, you need to understand it. C++ gives you the tools, now it's up to you to use them correctly. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one. Hello everyone and welcome back. In today's video we are diving deep into Dequel type, a powerful but sometimes misunderstood feature in modern C++. Whether you are new to the language or just looking to brush up on your understanding, this is one topic you will want to master. So let's get started. Let's begin with a simple question. What is Dequel type? Dequel type is a keyword in C++ that inspects the declared type of an expression without evaluating it and gives you that type at compile time. That means you can use it to deduce the exact type of a variable or an expression, which is incredibly useful when writing generic or template code. Here is a basic example to get us started. So what's happening here? We are declaring a as an int, and then we use Dequel type a to declare b. Since a is an int, the compiler sees Dequel type a as int, so b is also an int. This might seem trivial at first, but where Dequel type really shines is in more complex or generic contexts. Now let's think step by step about why Dequel type exists in the first place. Before C++11, if you had a complicated expression or function return type, you often had to manually write out the type. This could get very messy, especially with templates. With Dequel type, you can capture the exact type of an expression without repeating yourself or risking type mismatches. Here is a practical example involving functions. Even though add returns an int, we didn't need to know that. We just passed an example call to Dequel type and it gave us the correct return type. But here is where things get more interesting. Dequel type doesn't just give you the type, it gives you the exact type, including constness and reference qualifiers. Let me show you. This precision makes Dequel type very powerful in templates and metaprogramming. If you are writing a generic function and you want to return the same type as one of its inputs, you can use Dequel type to capture that type. Here is another real-world use case involving templates. In this template function, we want to return product of A and B. But what's the type of A times B? It could be anything, depending on what types you pass in, int, double, even user-defined types. Using Dequel type a times b, we can ensure that the return type matches the result of the expression. Let's take a moment to talk about a common gotcha. Dequel type does not evaluate the expression, it just looks at its type. That means you can safely write something like this. One last cool trick. If you want to get the type of a member of a struct, you can do that with Dequel type too. So to sum things up, Dequel type is an essential tool in modern C++. It helps you capture exact types at compile time, write more generic and reusable code, avoid manual type declarations and reduce errors, and work effectively with templates, functions and expressions. That's it for today's video. Thanks for watching. If this helped clarify things for you, Give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hello and welcome back to the channel. Today we are diving deep into one of the most versatile and powerful features in modern C++, lambda expressions. If you've ever seen those strange square brackets in C++ code and wonder what they were doing, or if you've heard people talk about capturing variables and got confused, this video is for you. We will walk through what lambdas are, how they work, when to use them, and some of the advanced features like captures, mutability, and generic lambdas. By the end of this video, you will have a solid understanding of how to use lambdas effectively in your C++ codebase. So what is a lambda? Let's start from the basics. A lambda expression is basically an anonymous function. It can be defined inline and used where you'd normally pass a function pointer or functor. They were introduced in C++ 11 and since then have become a core part of idiomatic C++ code. Here is a basic lambda. Let's break that down step by step. The square brackets part is called the capture clause. The normal braces is the parameter list. The curly brackets contains the function body. And the auto say hello just assigns the lambda to a variable, so we can call it like a normal function. So here we are creating a function that prints hello world and immediately calling it. Now let's see how parameters work. Easy, right? Lambdas behave just like regular functions, but they can also access variables from their surrounding scope using something called captures. Let's say you have a local variable and you want to use it inside a lambda. That's where the capture clause, the square brackets, comes in. Here is an example. Here we are capturing x by value. That means the lambda gets a copy of x at the moment it's created. Even if x changes later, the lambda still holds the original value. Now, what if we want the lambda to reflect changes to x? We can capture by reference. When you use x reference, any modification inside the lambda will affect the original variable. You can also capture everything by value or by reference using just an equal sign or just an ampersand sign inside the square brackets. This can be especially handy when using lambdas inside loops or STL algorithms. By default, lambdas that capture variables by value can't modify them. The captured values are const. But what if you want to modify a captured value inside the lambda? That's where the mutable keyword comes in. This outputs, even though we modified x inside the lambda, the original variable outside remains unchanged, because it was still captured by value, just not marked as const inside the lambda's body. Now let's talk about a very common and powerful use case, using lambdas with STL algorithms. For example, here is how you'd use a lambda with std_sort. The third parameter of std_sort is a comparator, and lambdas are perfect for that. You can define it inline, customize the logic however you like, and keep your code concise. You will also see lambdas used with std_foreach, std_transform, std_findif, and many other algorithms. Here is another example with std_foreach. This prints the square of each element. In C++ 14 we got generic lambdas. That means you can use auto in the parameter list. Behind the scenes, the compiler creates a separate function template for each type you use. This makes lambda super flexible and type safe. In C++ 20, you can even use template parameter lists inside lambdas, just like with regular templates. If you're writing a lambda inside the member function of a class, you might want to access this. Here is how you do it. Capturing this gives the lambda access to the member variables and functions of the object. As of C++ 17, you can even capture a this pointer by value to copy the current object into the lambda. One important thing to keep in mind when using lambdas inside loops is how captures behave. If you are capturing variables by reference and storing lambdas for later, you might end up with dangling references. For example, Why? Because I was captured by reference and its final value was free after the loop. Each lambda points to the same I. If you want to fix this, capture I by value. Now you will get 0, 1, 2 as expected. So let's summarize everything we've learned today. Lambdas are anonymous functions that you can define inline using square brackets, normal braces, curly braces syntax. You can capture variables by value or by reference using the capture clause. Use mutable if you want to modify captured values. Lambdas work beautifully with STL algorithms like sort, findif, and foreach. You can make generic lambdas with auto parameters. Inside classes, you can capture this to access member variables. Lambdas can make your code shorter, cleaner, and often faster. Once you start using them effectively, you will wonder how you ever wrote C++ without them. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one. Hey everyone, in today's video we are diving into a super important but often misunderstood topic in C++ architecture: interfaces. Specifically why and when to use them, and why it actually matters in real-world code bases. If you've ever looked at some C++ code and seen a class with only pure virtual functions, you were probably looking at an interface, whether the author called it that or not. But let's not get ahead of ourselves. Let's start from the beginning. What is an interface in C++? In C++, an interface is typically a class that contains only pure virtual functions, that is, virtual functions set to 0, and no data members. It looks like this. This class defines a contract. Any class that inherits from iShape promises to implement draw and area functions. That's the essence of an interface. A contract for behavior, not implementation. Now, the big question. Why not just write concrete classes and call them directly? The answer comes down to flexibility, decoupling, and testability. Let's say you are building a drawing application. You have multiple shapes, circles, rectangles, triangles, all of them need to be drawable. If your renderer is tied directly to circle or rectangle, you are baking in dependencies that will haunt you later. Instead, imagine this. Now, renderer can work with any object that satisfies the iShape interface. You are programming against an abstraction. That's powerful. And it's the kind of architectural thinking that separates small scripts from scalable systems. This is where things get interesting. Should every class have an interface? Absolutely not. Using interfaces too early or too often leads to unnecessary indirection. But there are clear situations where interfaces are the right tool. If you need to treat different classes uniformly, say you want to store a collection of different shapes, interfaces let you do that. No templates, no type erasure. Just classic polymorphism. When you want to decouple dependencies, imagine you are building a logging system, you could write this. But now you are hard-coding to std cout. Instead, you could define an interface. Now, file logger, console logger, network logger, all can implement ilogger. Your business logic doesn't care how the message gets logged. It just knows it can call log function. This is a big one. Interfaces allow you to inject mocks. Let's say you have a database class that implements an iDatabase interface. In tests, you can inject a fake test database that records calls instead of touching a real database. This makes your code unit testable. And in production systems, that's gold. Why interfaces matter? So far we have talked about how and when. Let's go deeper. Why does it matter at all? The short version: interfaces enforce separation of concerns. They prevent your high-level logic from depending on low-level details. This is the dependency inversion principle, one of the solid principles. The idea is high-level modules should not depend on low-level modules. Both should depend on abstractions. When you use interfaces, you are putting this principle into practice. Your application logic becomes more modular, more testable and more maintainable. Let's say you are making a 2D game. You've got game objects, enemies, bullets, players. All of them need to update and draw. You could do something like this. Each object implements update and draw functions. Now your main loop can look like this. You have created a clean, flexible architecture using interfaces. Now, a few things to watch out for. First, slicing. If you accidentally pass interface objects by value, you lose polymorphism. Always pass by reference or pointer. Second, no data members in interfaces. Interfaces should not contain data members, only behavior. They are meant to define what an object can do, not how it does it. If you find yourself putting fields in your interface, it's probably not an interface anymore. Avoid over-engineering. Not every class needs an interface. If a class is unlikely to be swapped or mocked, don't create an interface just because you can. Start concrete. Extract an interface only when you see real benefit, like decoupling or polymorphism. Interface versus template. Which one? In C++, you also have templates as a form of polymorphism. So when should you use interfaces and when templates? Use interfaces when you need runtime polymorphism. Use templates when everything can be resolved at compile time and performance is critical. Templates are great for things like std sort, where the type is known upfront. Interfaces shine when you don't know what you are dealing with until runtime, like user-loaded plugins or runtime configuration. So why and when to use interfaces in C++? Use them to define contracts. Use them to decouple systems. Use them to write better, testable, maintainable code. But don't overuse them. Start with concrete classes and introduce interfaces when you need flexibility or runtime abstraction. They are a tool, not a rule. If you use them well, your codebase becomes more resilient to change. You separate concerns, you isolate responsibilities, and you build software that lasts. That's why interfaces matter. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hello everyone and welcome back. In today's video, we are diving into one of the most impactful yet often underappreciated features introduced in C++20, constraint algorithms. If you've ever found yourself writing boilerplate code to make sure your algorithms only work with specific types, or if you've had a hard to diagnose error deep in template code, then constrained algorithms are something you will really appreciate. Today we will explore what they are, why they matter and how to use them effectively in modern C++. So what exactly are constrained algorithms? Let's start with the basics. Before C++20, most STL algorithms were implemented using function templates. These templates were extremely flexible, but that flexibility came at a cost. For example, if you accidentally try to pass a non-iterable object to std sort, you might get a compiler error, but not at the point of the call. Instead, you'd get a long, cryptic template error deep inside the STL headers. Not ideal. With C++20, constrained algorithms are now part of the standard. These are algorithms with constraints. That is, they are explicitly restricted to work with certain kinds of input types, using C++20's new concepts feature. Let's think step by step. Before C++20, you could write something like this. That works great, but if you accidentally wrote this, the compiler wouldn't immediately tell you that X isn't an iterator or even a container. Instead, you'd get a long and unhelpful error message about template instantiation. What constrained algorithms do is bring immediate, readable compile time feedback. In C++20, standard algorithms now have constrained versions that use concepts like std sortable, std ranges random access range, and more. Before we get deeper, we need to quickly explain concepts. Concepts are like type traits on steroids. They let you specify requirements for template parameters in a readable and enforceable way. Here is a simple concept. You can now write a template that only accepts incrementable types. If you try to call this with a type that doesn't support the ++ operator, the compiler tells you right away, and the error is actually readable. Concepts like this are exactly what constraint algorithms use behind the scenes. Now, let's look at the constraint algorithms in action. In C++20, algorithms were moved into a new namespace, std_ranges. So you now have two flavors of most algorithms. The classic STL version from stud, the new constraint range-aware version from std_ranges. Here is a classic sort again. And here is the constraint version. Notice the difference? You no longer need to pass iterators explicitly. The constraint algorithm understands that a vector is a random access range, and it uses the right overload internally. If you try to pass in something that's not sortable or doesn't meet the concept requirements, you get a clean and immediate compiler error. But why is this a big deal? Let's explore the advantages. First, better diagnostics. Using std_ranges sort with a bad type gives you a clear message that's much better than 50 lines of internal template noise. Second, it's safer and cleaner code. You don't have to manually pass iterators in many cases. Instead of worrying about the iterator, you just pass the container directly. Third, unified interface with ranges. C++20's ranges are more composable and expressive. Constraint algorithms fit perfectly into the ranges world, letting you chain operations more easily. Let's look at some examples and break them down, step by step. The first example is filtering and copying. Suppose we want to copy only even numbers from one vector to another. Using classic STL, we can write it like this. With constraint algorithms and ranges, we can do it like this. Cleaner, right? And if you pass a non-range, the compiler helps you immediately. Let's take a look how constraint algorithms are declared under the hood. Here is a simplified version of how std_ranges sort might be declared. This signature does a few things. Ensures that R is a random access range. Requires that its iterator is sortable with the given comparator and projection. Provides defaults for comparator and projection. You get strong guarantees before the algorithm even runs. Constraint algorithms often support an additional argument called a projection. This allows you to sort or search based on member of the object, without writing full comparator lambdas, for example in this code. The third argument, person age, is the projection. It tells the algorithm to compare using the age field. This feature makes code much more expressive and removes boilerplate. And when should you use constraint algorithms? If you are using C++20 or later, and especially if you are working with ranges, you should prefer the constraint versions. If you care about readable, compile time errors, they are a clear win. If you are working with custom types or generic code, constraint algorithms provide safety and clarity. That said, constraint algorithms do have some learning curve. The concepts behind the constraints can be intimidating at first, but they pay off quickly. Let's recap. Constraint algorithms in C++20 live in the std_ranges namespace. They make use of concepts to enforce correct usage at compile time. They simplify syntax by working directly with ranges and containers. They provide clear, readable error messages, making them easier to debug. They integrate naturally with other C++20 features, like projections and views. So while they might seem like just a small tweak at first glance, constraint algorithms represent a big step forward for safety, clarity and expressiveness in modern C++. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hey everyone and welcome back. In today's video we are diving into one of the most important sets of principles in software design, the solid principles, and how they apply specifically to C++. Whether you are working on embedded systems, high-performance game engines or modern desktop apps, Understanding Solid is crucial to writing clean, maintainable C++ code. Let's get into it. So, what is Solid? Solid is an acronym. Each letter stands for a principle that helps developers build systems that are easier to understand, change, test, and extend. These are S. Single Responsibility Principle. O. Open-closed principle. L. Liskov Substitution Principle. I. Interface Segregation Principle. D. Dependency Inversion Principle. Let's break each one down, see how it works in C++, and why it actually matters in the real world. Single Responsibility Principle. This one is simple but powerful. A class should have only one reason to change. What that really means is, a class should only do one thing, and do it well. Let's say we have a class like this. So this report class is doing two things: generating report data and handling file input-output. If requirements change for saving files, say we now need to support saving to cloud storage, we are forced to change this class, even though the generation logic didn't change at all. Instead, we should refactor like this. Now each class has one reason to change. This leads to lower coupling and better reusability. In C++, this also helps keep header files lightweight and compile times faster, which is always a bonus. Open-closed principle. Software entities should be open for extension, but closed for modification. That means if we need a new behavior, we should extend the existing code, not rewrite it. Here is a common anti-pattern. This design is fragile. If we add the triangle, we must modify draw shape. That's not closed for modification. A better way in C++ is to use polymorphism. Now, if we want to add triangle, we just create a new subclass. No need to touch the existing drawing logic. Open-closed works beautifully with virtual functions, but also with templates for zero-cost abstractions. Liskov Substitution Principle. This one is a bit trickier. Subtypes must be substitutable for their base types. So basically, it's valid C++ to create a derived object and assign it to a base pointer. But then, derived should behave in a way that doesn't break expectations. Here is an example that violates the principle. Now, if we write code that expects rectangle, this breaks if R is a square. Because the width and height are always equal, we have violated the principle. The takeaway: inheritance is not just code reuse, it's a contract. You must honor the base class behavior. In C++, this is why we often prefer composition over inheritance. Interface Segregation Principle. Clients should not be forced to depend on interfaces they do not use. In C++, this means we shouldn't create fat base classes with dozens of methods. For instance, this code. Let's say we now have a robot class. It needs to work, but doesn't eat or sleep. Now we are forced to stub those out. A better approach is to split this into smaller interfaces. Then a robot only implements iWorkable and the human can implement both. In C++, this keeps our object model clean and compilation units minimal, which helps build performance and code clarity. Dependency Inversion Principle. High-level modules should not depend on low-level modules. Both should depend on abstractions. This principle is all about decoupling. Imagine we have a report manager that directly creates a PDF exporter. Now report manager is tightly coupled to PDF exporter. We can fix this using an interface. Now report manager doesn't care how the report is exported, only that it can be. In C++, we can pass these dependencies via constructor injection or setter injection. And we can also use templates when we want to remove the runtime cost. So now you are all probably thinking, this is all great, but why does this matter specifically for C++ developers? Well, here is the thing. C++ gives you all the tools to write rock-solid architectures. templates, classes, RAII, inheritance, lambdas, you name it. But with great power comes the ability to make a mess very quickly. Solid gives you a mental framework to keep your code modular, testable, and future-proof. It helps reduce compilation dependencies by isolating responsibilities. It allows you to unit test components in isolation. And most importantly, it helps you write code that your future self or your coworkers won't hate. Even in performance-sensitive systems, like game engines, applying Solid in smart ways, like using data-oriented layouts or compile-time interfaces, can lead to better design without sacrificing speed. Alright, that was a deep dive into the Solid principles in C++. Each of these principles helps build a small piece of maintainable architecture, and when you apply them together, the result is powerful. If you are building real-world systems in C++, don't just think about how to write code. Think about why you structure it a certain way. That's it for today. Thanks for watching, and if you found this helpful, don't forget to like, subscribe, and check out the rest of the C++ series. Hey everyone, welcome back. Today we are diving into a topic that's super important when working with multi-threaded C++ programs: false sharing and cache line awareness. These two terms may sound like academic details, but trust me, they can have a big impact on your program's performance. By the end of this, you will know what false sharing is, how it happens, and most importantly, how to avoid it using simple techniques in C++. Let's get started. So, what is false sharing? To understand false sharing, we need to first talk about how modern CPUs handle memory. CPUs use caches, very fast memory that sits close to the CPU core. These caches load data from RAM in blocks called cache lines, typically 64 bytes in size. Now, here is the key. When two threads on separate cores access data that happen to lie within the same cache line, even if they are working on completely different variables, the CPU treats it as if they are sharing data. So if one thread writes to its variable, the other thread's CPU core sees that as a modification to the shared cache line and invalidates its own copy. That means it needs to reload the data from main memory or another core's cache, and this introduces latency. Let's look at a simple code example that demonstrates this problem. At first glance, it looks fine. We've got two threads incrementing two separate atomic variables. They are not accessing the same variable, so there shouldn't be any contention, right? But here is the catch. If A and B happen to lie on the same cache line, the CPU treats them as being in the same memory block. So every time thread 1 updates A, the cache line that holds both A and B is invalidated for thread 2, and vice versa. This constant back and forth creates what's called false sharing. It's false because the threads aren't really sharing data intentionally, but the hardware sees it differently due to how memory is physically laid out. So how do you fix this? You introduce padding, extra bytes that separate variables onto different cache lines. Here is how we do that. Now, A and B are guaranteed to be on separate cache lines because we have manually padded each one to occupy a full 64 bytes. This eliminates false sharing because no cache line is shared between them. You might be wondering, isn't this kind of micro-optimization premature? And the answer is not always. In high-performance computing, low-latency financial systems, or even general multi-threaded code that processes a lot of data in parallel, false sharing can kill performance. Let's take an example where this shows up very clearly. Imagine you have an array of structs, and each thread works on its own index. Now you spin up 4 threads, each passing its ID from 0 to 3. They are working independently. But guess what? These counter structs are likely stored contiguously in memory, which means some of them may fall on the same cache line. Boom, false sharing again. To fix it, we apply the same padding technique. Now each counter sits on its own cache line. No more unnecessary invalidations. Let's talk briefly about the align-as keyword. It's a C++11 feature that lets you specify alignment requirements for your struct or variable. Here we are aligning the struct to 64 bytes, the size of a typical cache line. You can also use stud hardware destructive interference size, which was added in C++17 to make this a bit more readable and portable. Same effect, cleaner syntax. Now, here is where cache line awareness really shines. When you design data structures with cache lines in mind, you reduce unnecessary contention and improve memory throughput. That means faster execution and better scalability when you add more threads. But it's not just about avoiding false sharing. Sometimes intentional sharing is good. For example, if multiple variables are always accessed together, placing them in the same cache line can improve spatial locality. But when they are accessed independently by different threads, you want to separate them. Let's say you are building a thread-safe queue. You have a head and the tail pointer, both atomics, used by producers and consumers. In a single producer, single consumer setup, the producer updates tail, the consumer updates head. These updates are frequent and independent. But again, if they are on the same cache line, it's going to hurt performance. Same story, it's false sharing. The fix? Now each member gets its own cache line. Problem solved. But be careful, don't just go throwing 64-byte paddings on everything. Padding adds memory overhead. Use it when it matters. Typically on hot paths where multi-threaded updates occur at high frequency. Also, cache line size isn't universal. 64 bytes is typical for a 64-bit system, but on some platforms it could be different. If you want to future-proof your code, use stud hardware destructive interference size to align or pad accordingly. Let's wrap this up with some takeaways. False sharing happens when threads access different variables on the same cache line. It leads to performance degradation due to cache invalidations and memory synchronization overhead. You can avoid it by aligning and padding variables so they reside on different cache lines. Use align-as 64 or stud hardware destructive interference size for safe and portable alignment. Don't overuse padding, apply it where profiling shows contention or where high-frequency updates happen. Cache line awareness is one of those low-level optimizations that becomes critical at scale. If you care about squeezing every drop of performance out of your multi-threaded C++ code, this is something you can't ignore. That's it for today. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hey everyone and welcome back to the channel. Today we are diving into a cool optimization hint introduced in C++20, the likely and unlikely attributes. These attributes allow you to give the compiler valuable hints about which branches of your code are more probable to be taken at runtime. In this video I'll explain what likely does, how it works, when you should use it, and just as importantly, when you shouldn't. Let's break it all down step by step. First things first, likely is an attribute that you can use to indicate that a particular path in your code is the most probable one to be executed. This is especially useful in if and switch statements, where the compiler can use this information to better optimize branch prediction. Here is an example. In this snippet, we are telling the compiler, hey, it's more likely that the user is already logged in, so optimize accordingly. Why does this matter? Modern CPUs are fast, but one thing they don't like is guessing wrong. When there is a conditional branch in your code, the CPU tries to predict which branch will be taken. If it guesses correctly, everything flows smoothly. If not, there is a pipeline stall, which costs performance. By using likely or unlikely, you are giving the compiler a hint so it can can organize the generated machine code to match expected runtime behavior. This helps the CPU make better branch predictions. There is also the unlikely attribute, which works exactly the same way, but for code paths that are rarely taken. For example, in this case, you are telling the compiler that it's unlikely this block of code will run, which helps it optimize the normal path better. How does this affect performance? It's important to understand that likely is a hint, not a command. The compiler can choose to ignore it if it thinks it knows better. Also, this doesn't change the logic of your code at all. It only affects performance in specific cases. That said, the gains can be noticeable in hot code paths where branching behavior has a measurable impact. For example, in tight loops that run millions of times, or in systems code where predictability is critical. You can apply likely and unlikely directly to conditional branches. This only applies to statements, not expressions or function declarations. Also, it's worth noting that if you write in the wrong place, the compiler will give you an error, so pay close attention to syntax. You shouldn't just sprinkle likely everywhere, hoping for speed boosts. If you misuse it, you might actually degrade performance instead of improving it. Worse yet, if your guess about what's likely is wrong in production, you are giving the compiler bad advice. So only use it when you are confident about the runtime behavior, or if you've profiled your application and found a clear hot path. Let's say you are building a web server. Most requests are handled without errors, but occasionally something goes wrong. In this example, you are telling the compiler that most of the time the request will be valid. Optimizing that case improves your server's responsiveness under normal conditions. To sum up, likely and unlikely are tools that help you guide the compiler's optimization decisions, but they should be used with care. They are most effective when used in performance-critical code where you understand the branching behavior. If used correctly, these attributes can shave off precious CPU cycles and improve the responsiveness of your application, especially under heavy load. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hello everyone and welcome back to the channel. In today's video we are diving into constexpr, a powerful feature in modern C++. It allows you to write faster and more efficient programs by evaluating code at compile time. Now, if you've ever wondered what constexpr means, when to use it and how it can make your code better, stick around because we are going to break it all down step by step. So what is constexpr? Let's start with the basics. The keyword constexpr stands for constant expression. When you mark a variable, function or even constructor as constexpr, you are telling the compiler, hey, this should be evaluated at compile time, if possible, especially in scenarios where you are doing a lot of repeated calculations or need values that will never change at runtime. Here is a very simple example. In this case, the function square is marked as constexpr, and since we are passing in a constant value of 5, the compiler computes the result during compilation. That means no actual calculation happens at runtime. It's as if you wrote the result's value directly. But why should you care? When code is evaluated at compile time, it reduces runtime overhead, it can make embedded and performance-critical systems much faster, and it can enable better optimizations by the compiler. Imagine you are programming for a microcontroller with limited CPU cycles. Every computation saved during runtime counts. Or maybe you are writing template-heavy C++ code where compile time values control how types or functions are generated. There is a common confusion between const and constexpr, so let's clear that up. Const means the value cannot change, but it might be determined at runtime. Constexpr means the value must be known at compile time. Here is an example. You can think of constexpr as a stricter and more powerful version of const. Starting from C++11, we could write constexpr functions, but they had to follow very strict rules. They had to have a single return statement, no loops, no local variables, and so on. But from C++14 onwards, the rules were relaxed. Now you can have local variables, loops, conditionals, and more. This makes const_expr much more flexible. Here is an example of modern const_expr function with a loop. You can now call this function in a const_expr context, and the compiler will evaluate it during compilation. No runtime cost. const_expr in classes. You can also use const_expr with constructors and member functions. You can now create const_expr objects like this. That's incredibly powerful. It means you can build entire object hierarchies that exist only at compile time. C++20 made const_expr even more useful. For example, now you can use try-catch blocks, dynamic memory allocation, and virtual functions in const_expr under certain rules. This pushes the boundaries of what you can compute during compilation. To wrap it all up, const_expr is one of those features that once you understand it, it changes how you think about writing C++. It leads to more predictable, efficient, and cleaner code. And as compilers get better and the language evolves, compile time computation is only going to get more powerful. So next time you are writing a helper function or defining a value that won't change, ask yourself, can this be const_expr? Thanks for watching, and if you found this helpful, don't forget to like, subscribe, and check out the playlist on the screen. See you next time. Hey everyone, and welcome. In this video, we are diving into an important concept in modern performance-critical programming: data-oriented design, or DoD, and how it applies to C++. This isn't just a buzzword, it's a mindset shift that's been critical in systems like game engines, simulations, and real-time applications. So let's explore what it is, why it matters, and how you can start applying it in your own C++ code. So what is data-oriented design? Traditionally, in object-oriented programming, we think about organizing code around real-world objects. We build hierarchies with inheritance, virtual methods, and polymorphism. That works well for modeling behavior. But what if the behavior isn't the bottleneck? What if data access is? That's where data-oriented design comes in. DoD is all about organizing data for how it's used, not how it looks conceptually. It's about understanding how the CPU works, especially the cache, and designing your data structures to take advantage of it. Let's break this down with a simple example. Imagine this C++ class. And let's say we have a vector of enemies that stores 10,000 of these. Now suppose every frame we loop over this vector to update positions based on velocity on every frame. That might look like this. Looks fine, right? Well, from a performance perspective, it's okay. But there is a problem here that DoD addresses directly: the CPU cache. Modern CPUs are fast, but memory is slow. To speed things up, processors use cache lines, small chunks of memory loaded into the CPU. When data is contiguous and frequently accessed, the cache helps a lot. In our example, each enemy object has 5 or 6 variables, but we only use 4 of them during the position update. So for every enemy, we are pulling the whole struct into the cache, including health and is alive, which are not needed for movement. Multiply that overhead by thousands of objects, and you start wasting cache space and memory bandwidth. DoD solves this by separating data based on how it's used. Let's refactor this with DoD in mind. Instead of a vector of structs, we use separate arrays for each component. Now, when we update movement like this, we are only accessing the data we need, and it's tightly packed. This means fewer cache misses, more efficient use of memory, and faster execution. This isn't just theory, it can be orders of magnitude faster, especially at scale. So why does this matter in C++ specifically? Because C++ gives you direct control over memory layout. Unlike many higher level languages, you can choose exactly how and where data is stored. That's a superpower. And with great power comes the need to use it well. Data-oriented design aligns beautifully with C++ features like std-vector for tightly packed arrays, manual memory management when needed, SIMD optimizations, and cache-aware design. You can even go further with things like entity component systems, which are common architecture in game engines using DoD principles. So, how do you know when to apply DoD? Not every program needs it. If you are building a GUI app or something, depending on input-output, DoD won't change much. But in real-time systems, games, physics simulations, high-frequency trading, or even signal processing, data layout becomes a primary performance factor. Here are some signs DoD might help. You have large collections of data-heavy objects. You are iterating over them in tight loops. Performance profiling shows memory stalls or cache misses. Most of your CPU time is spent reading or modifying object state. If that sounds like your use case, DoD is worth a look. Let's talk trade-offs. Data-oriented design isn't free. It can make code less intuitive, especially at first. For example, in object-oriented programming, we might write this. But in a data-oriented design system, damage might be processed in a batch across arrays. That's more verbose and less encapsulated. Also, DoD tends to favor data pipelines over object hierarchies. If your team is used to traditional object-oriented programming, it can be a mental shift. You may end up writing more boilerplate and organizing systems around access patterns rather than domain logic. But if performance matters, really matters, the gains are worth it. You don't need to refactor your whole code base. Start small. Identify a tight loop in your game or simulation. Use a profiler. Look for hotspots. Then try separating your data, just that one part, into a structure of arrays. Then run the profile again. You will probably see measurable gains. That success can build momentum to try it elsewhere. Let's talk about C++ 17 and C++ 20 features that help with DoD. StdSpan allows safe views over raw arrays, enabling cleaner structure of array access. Std ranges and views can be used to process data in a functional pipeline style. Lambdas help organize behavior in data processing loops. Const expressions and templates can enable compile time layout optimizations. And std tuple or structured bindings can help group logic while keeping data separate. Modern C++ gives you powerful tools to write expressive, fast and cache-aware code, if you design with the data in mind. Let's wrap this up with some key takeaways. Data-oriented design is about organizing code around how data is used, not how it's modeled conceptually. The CPU cares deeply about memory layout, especially contiguous access patterns. Separating your data, like moving from array of structures to structure of arrays, can yield big performance improvements. C++ is uniquely suited for DoD because it exposes low-level memory control. You don't need to go full DoD everywhere. Start where it matters. Remember, the goal isn't to abandon clean design. It's to align design with performance realities. Thanks for watching, and if you found this helpful, don't forget to like, subscribe and check out the rest of the C++ series. So what is cache locality and why does it matter in memory management? Let's break it down step by step. In modern computer systems, memory is organized in a hierarchy. At the top, you have the fastest memory, the CPU registers and caches. Then you have the RAM, and finally disk storage. The closer you are to the CPU, the faster the memory access. But also the smaller and more expensive the memory is. Now, the CPU cache plays a critical role in performance. It stores small chunks of memory that the CPU is likely to access soon. This is where cache locality comes into play. There are two types of cache locality: Temporal and spatial. Temporal locality means that if a piece of data is accessed once, it's likely to be accessed again soon. Spatial locality means that if a piece of data is accessed, nearby data will likely be accessed soon too. Let's see a C++ example to make this clearer. Suppose we have two loops that do the same logical operation but access memory differently. This code has good spatial locality. Why? Because C++ stores 2D arrays in row major order, meaning matrix ij and matrix ij+1 are next to each other in memory. So when we move across columns inside a row, we are accessing contiguous memory. Compare that with this. This time we are jumping across rows for every column. So we are accessing memory in a way that breaks spatial locality. Even though we are doing the same computation, this version will be slower because of more cache misses. Cache misses happen when the data the CPU needs isn't in the cache, so it has to go fetch it from main memory. That's hundreds of cycles slower. Good cache locality reduces cache misses and boosts performance significantly, especially in large data processing tasks. Another common scenario is with structs and classes in C++. Consider this example. If we loop over the particles array and update positions and velocities, we will benefit from spatial locality, because each particle is stored contiguously in memory. But let's say we change the design and do this instead. This is called a structure of arrays versus the previous array of structures. Depending on what operations we are doing, structure of arrays can be more cache friendly. For example, if we are only updating velocities. In this case, all access data is packed together in one array, improving cache efficiency. With array of structures, we would be skipping over x, y and z to get to each velocity, which may cause more cache misses. So designing data structures with cache locality in mind can make a huge difference. Another thing to consider is memory alignment. Misaligned data can span multiple cache lines and hurt performance. Modern compilers and CPUs can sometimes fix this, but you can also use alignment attributes in C++ like this. This ensures the struct starts at a 64-byte boundary, which matches common cache line sizes. To wrap it up, cache locality is about accessing memory in a way that makes the most of the fast CPU caches. It's all about how your data is laid out and how you access it. By being cache conscious in your code, like choosing the right loop order, struct layout and memory access pattern, you can write much faster, more efficient C++ programs. Thanks for watching. Hey everyone, welcome back. Have you ever wondered how memory allocation works under the hood in C++? Or why some applications feel snappy and efficient while others are sluggish despite similar logic? Today, we are diving deep into custom allocators in C++, what they are, why they matter, and how they can give you fine-grained control over memory management in your programs. Let's start with the basics. What is an allocator? In simple terms, an allocator is a policy object that handles memory allocation and deallocation for containers like std_vector, std_list, and others. By default, the C++ standard library containers use std_allocator, which allocates memory from the heap using new and delete. But sometimes, we need more control over how memory is allocated. That's where custom allocators come into play. Let's visualize this with a simple example. This works fine, but behind the scenes, every time the vector resizes or reserves memory, it calls the default allocator to get memory from the heap. Now, imagine you are building a real-time system or a game engine where performance is critical. You don't want frequent heap allocations, they are slow and can cause fragmentation. Custom allocators let you use memory pools, avoid frequent allocations and deallocations, align memory for SIMD instructions, track allocations for debugging, and improve performance and determinism. In performance-sensitive environments, these benefits can be game-changing. Let's say you want to allocate all memory from a pre-allocated buffer, a memory pool. With a custom allocator, you can do just that. Here is a super simplified custom allocator that allocates from a static array. Here is its usage. This is a very crude example. We are not handling deallocation or alignment here, but it gives you the idea. To make custom allocators compatible with STL containers, it needs to define certain members, like a value type member, the allocate function, the deallocate function, and a copy constructor template. Most of the complexity comes from making it work with STL containers that copy and rebind allocators across types. In C++17 and beyond, the allocator model has become simpler, but the general structure remains the same. Let's take a look at a more realistic example that also supports the allocation. You can now use this allocator with standard containers. Why not just always use a custom allocator? That's a good question, but custom allocators add complexity. For general applications, the default STUD allocator is fast and optimized. But in real-time systems, embedded programming, financial trading platforms, or high-performance games, where every cycle counts, custom allocators provide predictability and performance. Another reason: debugging. You can write a custom allocator that logs all allocations. Now you can see exactly when and how often allocations happen. Let's talk about real use cases where custom allocators really shine. Memory pools. In a game you might allocate 1000 entities at the start. Instead of allocating them one by one from the heap, a pool allocator grabs a large chunk once and carves out space as needed. Second, arena allocators. You pre-allocate a big chunk of memory and allocate from it linearly. When done, you reset the whole arena. It's fast and avoids fragmentation. Third, stack allocators. Memory is allocated and freed in a strict LIFO order. Last in, first out, just like a call stack. Perfect for temporary allocations. Fourth and last, shared memory or custom heaps. Allocators can be built to allocate from shared memory or GPU memory, or even custom OS-provided heaps. Important to note, not all STL containers use allocators the same way. For example, StudList allocates each node separately. A pool allocator makes a huge difference here. But StudVector grows its capacity exponentially and uses realloc style behavior. Allocator efficiency may vary. Also, when containers are copied, STL may copy or rebind the allocator depending on the allocator's propagation traits, especially in C++11 and later. You can write your own classes to be allocator aware. For example, this way, your custom types can benefit from the same allocation strategies as STL containers. Ever had a memory leak or a mysterious crash? Custom allocators can help track number of allocations, size of allocations, leaks, and dangling pointers. By overriding allocate and deallocate, you gain full visibility into what's happening at runtime. C++ gives you the tools to manage memory precisely. The allocator system is part of that toolbox. When you use a custom allocator, you take control of one of the most fundamental parts of your program, the memory. It can lead to more efficient, more predictable, and more robust software, especially in systems where performance or resource constraints are critical. Should you use custom allocators for every project? Absolutely not. But understanding them gives you an edge, and the power to optimize when it really matters. If this helped clarify things for you, give the video a like, subscribe, and check out the playlist on the screen. See you in the next one. Hey everyone and welcome back. In this video, we are diving into a really powerful design principle in software architecture, the open-closed principle, specifically in the context of modern C++. Let's go step by step. The open-closed principle comes from the solid principles, 5 fundamental rules that help us write better, more maintainable software. The open-closed principle says, software entities should be open for extension, but closed for modification. That sounds abstract, so let's break it down. It means that you should be able to add new behavior without changing existing code. We want to extend functionality, not modify what already works. Why is this important? Because changing working code introduces bugs. It breaks things. It's risky, especially in large code bases. If we can add features without touching existing logic, we get safer and more modular designs. Let me show you a problem that violates the open-closed principle. Imagine we are working on a simple reporting tool. We have a class that calculates area of shapes. Here is a basic version. Seems fine, right? Now, if your manager says, "Hey, we need to support triangles," what do? We go back to area calculator and add more code. This violates the open-closed principle. Every time a new shape is added, we are modifying area calculator. That's not scalable. Eventually, this class becomes bloated, and every edit risks breaking something else. Let's refactor this using polymorphism. We define a base class called shape, and each shape subclass will override a virtual method to calculate its area. Now let's make rectangle and circle inherit from shape. And now our area calculator doesn't need to care about the types of shapes at all. If we now want to add triangle, we just create a new class. No changes to area calculator. That's the open-closed principle in action. It's open for extension, we can add new shapes, but it's closed for modification. We didn't have to touch area calculator. This idea becomes even more important in real-world scenarios. Let's take a real example from a game engine. Let's say you have an entity class, and every system operates on it: rendering, physics, audio. Initially, you might hardcode some logic like this, but adding a new entity type, you modify this function again. A better design would be to define a renderable interface, and each entity implements its own render logic. Then your renderer simply calls the draw function polymorphically. This keeps your renderer untouched, even as new entity types are added. Now, there is a caveat. Sometimes the open-closed principle leads to too much abstraction, especially in C++. Virtual functions, base classes, and interface hierarchies can become over-engineered. In modern C++, there is an alternative: type erasure. Let's say you want polymorphism without inheritance. Here is a sketch using stud function. Now, any object, lambda, functor, or function can be wrapped into a renderable. You don't need a base class. This is lightweight and powerful. And it still follows the open-closed principle. You can add new types and draw logic without changing any central renderer class. So when should you apply the open-closed principle? When a module is used by many parts of the codebase. When you are expecting frequent change in features or requirements. When a system must support plugins or extensions without recompiling core logic. And when should you avoid it? If a piece of logic is unlikely to change. Don't introduce unnecessary abstraction for small, local systems where code clarity is more important than reuse. As always, it's about a balance. The goal is not to follow principles blindly, but to understand when and why they help. Let's summarize. The open-closed principle helps you write code that is easier to extend and harder to break. In C++, this often means using inheritance and virtual functions to abstract behavior, leveraging modern alternatives like type erasure or templates, designing modules to depend on interfaces, not concrete types. By following this principle, you reduce the risk of regression bugs, encourage reuse, and write more robust, flexible code. Thanks for watching. I hope this gives you a clearer picture of the open-closed principle in C++ and why it's such a valuable tool in clean software design. If you found this helpful, don't forget to like, subscribe, and check out the rest of the C++ series. See you next time. Hello everyone and welcome to today's video where we dive into another powerful feature introduced in C++20, const-eval. This is a keyword that might look simple, but it has deep implications for compile-time programming in C++. In this video we will explore what const-eval means, how it differs from const-expr, and how you can use it effectively in your own code. Let's start by understanding the motivation behind it. In C++, we've had const-expr since C++11. It allows us to evaluate functions at compile time if possible. That's the key phrase. If possible. But what if you want to enforce that a function must be evaluated at compile time? That's exactly where const-eval comes in. When you mark a function with const-eval, you are telling the compiler that this function must be evaluated at compile time. No exceptions. If you try to call it in a context where compile time evaluation is not possible, the compiler will throw an error. Let's look at a simple example. This function is now guaranteed to run at compile time if you try to call it like this. This works because the argument 5 is a constant and the result can be computed at compile time. But if you try this, the code will not compile. The compiler will complain because getValue is not a constant expression, and const-eval requires that all its inputs and outputs are fully known at compile time. Let's think step by step about what this means for you as a developer. Const-eval gives you a guaranteed compile time evaluation. This is extremely useful in scenarios like metaprogramming, compile time validation, and generating lookup tables or other data structures that should not have any runtime overhead. Now let's compare it to const-expr, because this is where a lot of confusion happens. A const-expr function can be evaluated at compile time if given constant inputs. A const-eval function must be evaluated at compile time, or your code won't compile. You might use const-expr when you want flexibility. Maybe sometimes runtime is fine, and other times compile time is better. But you'd use const-eval when runtime calls are simply unacceptable. Here is an example where const-eval helps enforce constraints. This is useful for library authors and developers working on embedded systems or performance-critical applications. It ensures that invalid inputs are caught at compile time, not at runtime when it might be too late. Another thing to note is that const-eval functions cannot have any side effects. You can't use them to write to output streams or modify global state. That's because they are part of the compile time world, and everything must be pure and deterministic. Let's see how you might use it in practice. This is a classic case of metaprogramming, but it's much clearer and safer using const-eval. To wrap up, const-eval gives you precise control over compile time logic. It's stricter than a const-expr, but that strictness can be exactly what you need when writing safe and efficient code. That's all for today's video. I hope this helped clarify what const-eval does and how to use it. If you learned something new, feel free to like, subscribe, check out the playlist on the screen, and I will see you in the next one. Hello everyone and welcome to this deep dive into object lifetime in C++, where we will explore a powerful but often overlooked optimization called empty base optimization, or EBO. We will also talk about why it matters in terms of memory efficiency, object layout, and performance-critical C++ systems. Let's get into it. In C++, every object must occupy a unique memory address. Even if a class has no data members, it must still consume at least 1 byte of memory. This ensures that different objects of the same type don't alias the same address. Here is an example. Even though empty has no data, E1 and E2 each get a unique address. Why? Because the standard requires that two distinct objects occupy different locations. Let's verify the size of an empty struct. 1 byte. That's the cost of being empty. But now imagine this. What if you are building a class that inherits from an empty base? Would it still take up that extra byte? This is where empty base optimization kicks in. Let's see how. If EBO is enabled, and in almost all modern compilers it is, then derived will only be the size of an int, not an int plus 1 byte. The compiler is allowed to treat the empty base as taking up no space. This is key to optimizing object layout. Why does this matter? Imagine you are designing a class with policy-based design or traits. For example, take this code. If policy is empty, empty base optimization makes it free in terms of memory. You can now use tag dispatching or behavior injection at zero runtime cost. Let's make it more interesting with two policies. If both P1 and P2 are empty, empty base optimization lets the combined object still be the size of just an int. But there is a catch. Empty base optimization only works when the empty base is not repeated. If the same empty class appears multiple times in the inheritance chain, the compiler must assign each a unique address unless it's explicitly optimized away. Here is a problematic case. Here empty appears twice, once in A and once in B. This leads to ambiguity and disqualifies EBO in many cases. You get what's called the diamond problem. To resolve this, you would need virtual inheritance or redesign. Now let's talk about a real-world use case, the std function implementation. It uses type erasure internally and often stores functors or function objects. Sometimes these functors are stateless. With EBO, storing a stateless functor doesn't take up extra space. That means calling a lambda that captures nothing is as cheap as a regular function pointer. Internally, the lambda is empty. Thanks to EBO, function uses minimal memory for storage. Another key use of EBO is in std tuple. Let's look. Despite having two elements, the size of t is still the size of an int, assuming EBO is applied. That's an optimization that you get for free, just by designing your types with EBO in mind. So how do you leverage EBO in your own types? The simplest way is to inherit from empty types, instead of embedding them. Here is an example. This way, if t is empty, EBO can kick in and eliminate its storage overhead. Compare that to this. Here, even if t is empty, the compiler must still allocate space for it, because it's not in the base subobject. There is another variation of this idea, used by the standard library and others, compressed pair. A compressed pair is a pair that uses EBO for one or both of its elements, depending on whether they are empty. Let's say you write something like this. If t1 or t2 is empty, the pair still consumes minimal space. This is a great trick for STL-like containers or adapters that carry allocators or predicates which might be stateless. Of course, you need to be careful with multiple inheritance and ambiguity, especially if both t1 and t2 are of the same empty type. A common way to solve this is to introduce tagging. This makes each base unique and EBO safe, even if t is the same type. But what about visibility? EBO often works best with private inheritance, because it avoids exposing the base class's interface, which might not be desirable in a compressed object. Now let's briefly consider object lifetime. Since empty bases can be optimized away, does that mean their constructors or destructors are also omitted? No, it does not. The compiler still calls constructors and destructors of empty base classes, unless they are trivial. EBO only affects memory layout, not the semantic behavior of your code. So if you rely on side effects in your base constructors, you are still safe. Even if logger is empty in terms of data, the constructor runs and prints the message. So remember, EBO is layout optimization. Lifetime semantics remain unchanged. Let's recap quickly. In C++, even empty classes take up space due to object address rules. EBO allows the compiler to eliminate the space overhead of empty base classes. It's a powerful technique used in the STL, std tuple, std function, allocators, and more. To leverage EBO, inherit from empty classes instead of embedding them. Watch out for multiple inheritance of the same empty class. Tagging can help. EBO doesn't affect constructor or destructor calls. Object lifetime remains fully honored. EBO is a subtle but crucial part of writing memory-efficient C++. Once you understand it, you start to see how libraries like the STL pull off their zero-cost abstractions. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hey everyone, welcome back. In today's video, we are diving into the Single Responsibility Principle, often abbreviated as SRP, and how it applies in C++. This is one of the 5 solid principles of object-oriented design, and it's an incredibly important one to get right when you are building scalable, maintainable software. Let's start with the basics. What is the Single Responsibility Principle? The formal definition says a class should have only one reason to change. In simpler terms, that means every class or module in your code should only do one thing, and it should do that one thing well. Now, in C++, this can be tricky. It's easy to create big classes that do a little bit of everything, especially when you are in a rush or building prototypes. But over time, those classes become harder to test, harder to maintain, and much more likely to break when you change them. Let's walk through a simple example to see what a violation of SRP looks like. Here we have a class called report. It can generate the report, save it to disk, and also send it over the network. On the surface, this might seem convenient. Everything is in one place. But this class is violating the Single Responsibility Principle. Why? Because it has multiple reasons to change. If the format of the report changes, that affects generate report. If the file system changes, or we switch to using a database, that affects save to file. And if the network protocol changes, that breaks send over network. Each of these behaviors represent a separate responsibility. Let's refactor this class to follow SRP more closely. We will spit out each concern into its own class. Now we have 3 small classes. Report is only responsible for generating the report content. File saver handles saving data to disk. Network sender takes care of communication. Each class has a single reason to change, and that's exactly what SRP is about. This is also a lot easier to test. For example, if we want to write a unit test for report generation, we don't have to worry about mocking file input-output or network calls. So why does this matter in real-world C++ code? Let's think about the types of bugs we run into when violating SRP. One classic issue is that a change in one area unexpectedly breaks another. You update the file saving logic to handle UTF-8 properly, and suddenly the report generation stops working. Why? Maybe a shared buffer changed format. This kind of coupling is what SRP is designed to avoid. It also matters for team collaboration. If one developer is working on the file saving logic and another is modifying the report format, and both changes affect the same class, you are going to have merge conflicts and poor cohesion. With SRP compliant design, multiple people can work independently with minimal interference. Now I want to be clear. SRP is a guideline, not a hard rule. You don't need to obsessively split everything into 1,000 classes. But when you find a class doing several unrelated things, it's a strong signal that it's time to refactor. Let's look at another example, this time from a more practical C++ domain. Logging. Here is a simple logger class that writes messages to a log file and also supports different log levels. Seems okay, right? But what happens when we want to add new output options, like logging to the console or a remote server? Or maybe we want to change the formatting of the log entries. Each of these changes affect the same class. So again, we are breaking SRP. Here is how we might apply SRP to this. Now the responsibilities are clearly separated. Log formatter decides how the messages look. File writer decides where the message goes. Logger coordinates the two. Want to add console output? Just create a console writer. Want JSON formatting? Swap in a new formatter. The core Logger class doesn't change. That's the power of SRP. It makes your code modular, testable, and open to extension, but close to modification. That's also touching on the open-closed principle, which we already covered in a video. Now, some of you might be thinking, doesn't this create a ton of small classes? Isn't that over-engineering? Great question. And the answer is, it depends. If your project is small, maybe 1 or 2 classes doing multiple things is fine for now. But if your application is expected to grow, or you are working with a team, or you are doing unit testing, then SRP starts paying off really quickly. In C++ especially, this helps you reduce header dependencies, minimize rebuild times, and prevent fragile base class problems. So it's not just a design philosophy. It has real tangible benefits in C++ development. To wrap up, the single responsibility principle says a class should have only one reason to change. In C++, this helps you create modular, reusable, and maintainable code. It improves testability and reduces unexpected side effects. And it makes working in teams much more manageable. Start looking at your classes with these lenses. What are all the reasons this class might need to change? If the list has more than one item, it's time to refactor. Alright, that's it for today's episode on SRP. Thanks for watching, and if you found this helpful, don't forget to like, subscribe, and check out the playlist on the screen. See you in the next one. Hello everyone, and welcome back to the channel. In today's video, we are going to dive into another feature from C++20, constinit. You might have heard of it, or even confused it with constexpr or const, but don't worry, we are going to break it down clearly, step by step. So you'll walk away understanding exactly what constinit does, why it exists, and how to use it properly in your own C++ code. Let's start with a simple question. What problem is constinit trying to solve? To understand this, we need a quick refresher on static and global variables in C++. These variables have static storage duration, meaning they exist throughout the lifetime of the program. However, when they are initialized, can vary. In C++, static and global variables can be initialized at compile time or at runtime. When something is initialized at runtime, it's done before main starts, but the order in which this happens across translation units is undefined. This is known as the static initialization order fiasco, and it can cause subtle and dangerous bugs in your programs. Here is a quick example. This is a runtime initialization. If another file depends on global var during its own static initialization, things can go wrong, especially if getValue function returns a value depending on other global state. So how do we avoid this? That's where constinit comes in. Constinit is a keyword introduced in C++20 that requires a variable with static storage duration to be initialized at compile time. If it can't be initialized at compile time, the code will fail to compile. In other words, constinit guarantees initialization happens at compile time, preventing the risk of undefined initialization order at runtime. Here is an example. This tells the compiler, make sure safe global is initialized at compile time. If it can't be, stop the build. So what's the difference between constinit and constexpr? Let's break it down. Constexpr means the value must be known at compile time and the variable must be constant. Constinit only requires that initialization happens at compile time, but the variable can still be mutable, for example in this code. So constinit is useful when you need static variables initialized at compile time, but don't want them to be constant for the lifetime of the program. Let's look at a common use case. Singleton pattern with static local variables. This ensures that instance is initialized at compile time, avoiding runtime surprises. This is especially helpful in embedded systems or low-level applications where startup behavior must be predictable. Now, here is the important caveat. Constinit does not imply constness. You can still modify a constinit variable after initialization. Also, you cannot use constinit on variables that are not static or global. This makes sense. It's only meant for compile time initialization of variables that live for the duration of the program. Here is a quick summary of when to use what. Use const for read-only variables. Use const_expr when you want the value known at compile time and never changeable. Use constinit when you want a variable initialized at compile time but still want to be able to change it later. To wrap things up, constinit helps you write safer, more predictable C++ code by eliminating the static initialization order problem. It's not a replacement for const or const_expr. It's a tool for a very specific job, and when used correctly, it can save you from some really hard to find bugs. Thanks for watching. If this helped clarify things for you, give the video a like, subscribe and check out the playlist on the screen. See you in the next one. Hey everyone and welcome back to the channel. Today we are diving into something that might sound like a buzzword at first, but it's actually a foundational concept in software design: layered architecture. And we are going to look at it through the lens of C++. So what is layered architecture and why should a C++ developer like you care? Let's get into it. Imagine you are building a fairly standard application. Maybe it's a game, a business app, or a networked service. As it grows, you notice that your logic, your input-output, your rendering, your database access, they all start to blur together. You are editing files that talk to too many parts of the system. Changes in one place randomly break others. Debugging becomes a nightmare. That's where layered architecture comes in. It gives us structure. It's about organizing our code into logical layers of responsibility. Each layer has a specific purpose, and ideally, it should only communicate with the layer directly above or below it. So, how many layers are we talking about? Well, that depends on your needs, but most systems use 3 or 4. Presentation layer handles input-output, UI or user interaction. Application layer orchestrates operations like what happens when you click a button. Domain or business logic layer contains the actual rules of your system. Data access layer deals with databases, file systems, or external services. Let's see this with a simple example in C++. Let's say we are building a banking application. Our user wants to transfer money from one account to another. How can we lay this out? First, we will define the domain layer. This is the core. It knows what an account is and how a transfer should work. This layer should have no idea how the data is stored or where input comes from. It just defines what the system does. Now, above that, let's build the application layer. This layer uses our domain logic to coordinate tasks. This service fetches the accounts from a repository, applies the logic, and saves the updated data. We haven't implemented that repository yet. Hold on to that though. Now, at the top, there is the presentation layer. This might be a console app, GUI, web API, whatever talks to the user. Notice how main doesn't know what an account is doing inside. It just invokes the service. Now, let's go back to the data access layer. Here is where we define account repository, maybe as an interface. Then, we implement that using a file or a database. That's 4 clean layers. Each has a role. The main function doesn't talk to accounts directly. The accounts don't care how they are saved. The transfer logic only knows how to use repositories, not how they are implemented. So why does this matter? Let me give you 3 reasons. First, separation of concerns. Each layer focuses on one job. This makes the code easier to understand, test, and maintain. You can look at one file and generally know what kind of logic to expect. Second, Loose coupling. We are using interfaces between layers, like account repository to isolate details. That means if we later move from file storage to a SQL database, only the repository implementation changes. The rest of the system stays untouched. Third and final, easier testing. You can mock the data layer and test just the business rules. Or you can test the service layer without involving the UI. It's modular. That's powerful in large systems. This isn't magic, it's a design approach. Let's talk about its trade-offs. Layered architecture adds complexity. For small applications or quick prototypes, it might feel like overkill. Writing interfaces, abstracting repositories, this can be extra work if your project is only a couple of files. Also, if you are not careful, the boundaries between layers can start to blur. People might start calling data access from UI code, or mixing logic into repositories. Stick to the rule. Only communicate with adjacent layers. Another tip. Use dependency injection between layers. Instead of creating objects directly, inject them through constructors or factories. This makes your layers more flexible and testable. For example, like this. That means you could later replace repo with a mock repository when you need testing. See how clean that is? Also, C++ gives you the tools for this kind of architecture. Interfaces via abstract classes, ownership via smart pointers, modular builds with headers and separate translation units. But you have to practice discipline. C++ won't stop you from breaking the rules. Unlike some managed languages, there is no built-in framework for layering. It's all up to you how you organize your code. When should you use layered architecture? When your app is growing and you want to future-proof it. When you need testable code. When you have multiple developers working in parallel. Layers help define clean boundaries. When you are doing domain-driven design or building something with business rules that might evolve. But again, if you are writing a quick CLI tool or a script-style utility, it's okay to keep things flat. Use your best judgment. To wrap up, layered architecture is about separating your code into meaningful layers: presentation, application, domain, and data. It keeps each part of the system focused, testable, and adaptable. It's not just for web or enterprise code bases. It works beautifully in C++ too, especially when you value maintainability and clarity. Next time you are about to mix UI code with logic, pause and ask yourself, would this be clearer if I split it into layers? Chances are the answer is yes. Alright, that's it for this one. Thanks for watching, and if you found this helpful, don't forget to like, subscribe and check out the rest of the C++ series. Hey everyone and welcome. In this video we are diving into an important concept in modern performance critical programming: data-oriented design, or DoD, and how it applies to C++. This isn't just a buzzword, it's a mindset shift that's been critical in systems like game engines, simulations and real-time applications. So let's explore what it is, why it matters, and how you can start applying it in your own C++ code. So what is data-oriented design? Traditionally, in object-oriented programming, we think about organizing code around real-world objects. We build hierarchies with inheritance, virtual methods, and polymorphism. That works well for modeling behavior. But what if the behavior isn't the bottleneck? What if data access is? That's where data-oriented design comes in. DoD is all about organizing data for how it's used, not how it looks conceptually. It's about understanding how the CPU works, especially the cache, and designing your data structures to take advantage of it. Let's break this down with a simple example. Imagine this C++ class. And let's say we have a vector of enemies that stores 10,000 of these. Now suppose every frame we loop over this vector to update positions based on velocity on every frame. That might look like this. Looks fine, right? Well, from a performance perspective, it's okay. But there is a problem here that DoD addresses directly. The CPU cache. Modern CPUs are fast, but memory is slow. To speed things up, processors use cache lines. Small chunks of memory loaded into the CPU. When data is contiguous and frequently accessed, the cache helps a lot. In our example, each enemy object has 5 or 6 variables, but we only use 4 of them during the position update. So for every enemy, we are pulling the whole struct into the cache, including health and is alive, which are not needed for movement. Multiply that overhead by thousands of objects, and you start wasting cache space and memory bandwidth. DoD solves this by separating data based on how it's used. Let's refactor this with DoD in mind. Instead of a vector of structs, we use separate arrays for each component. Now, when we update movement like this, we are only accessing the data we need, and it's tightly packed. This means fewer cache misses, more efficient use of memory, and faster execution. This isn't just theory, it can be orders of magnitude faster, especially at scale. So why does this matter in C++ specifically? Because C++ gives you direct control over memory layout. Unlike many higher level languages, you can choose exactly how and where data is stored. That's a superpower. And with great power comes the need to use it well. Data-oriented design aligns beautifully with C++ features like stud vector for tightly packed arrays, manual memory management when needed, SIMD optimizations, and cache-aware design. You can even go further with things like entity component systems, which are common architecture in game engines using DoD principles. So how do you know when to apply DoD? Not every program needs it. If you are building a GUI app or something, depending on input-output, DoD won't change much. But in real-time systems, games, physics simulations, high-frequency trading, or even signal processing, data layout becomes a primary performance factor. Here are some signs DoD might help. You have large collections of data-heavy objects. You are iterating over them in tight loops. Performance profiling shows memory stalls or cache misses. Most of your CPU time is spent reading or modifying object state. If that sounds like your use case, DoD is worth a look. Let's talk trade-offs. Data-oriented design isn't free. It can make code less intuitive, especially at first. For example, in object-oriented programming, we might write this. But in a data-oriented design system, damage might be processed in a batch across arrays. That's more verbose and less encapsulated. Also, DoD tends to favor data pipelines over object hierarchies. If your team is used to traditional object-oriented programming, it can be a mental shift. You may end up writing more boilerplate and organizing systems around access patterns rather than domain logic. But if performance matters, really matters, the gains are worth it. You don't need to refactor your whole code base. Start small. Identify a tight loop in your game or simulation. Use a profiler. Look for hotspots. Then try separating your data, just that one part, into a structure of arrays. Then run the profile again. You will probably see measurable gains. That success can build momentum to try it elsewhere. Let's talk about C++ 17 and C++ 20 features that help with DoD. StudSpan allows safe views over raw arrays, enabling cleaner structure of array access. Stud ranges and views can be used to process data in a functional pipeline style. Lambdas help organize behavior in data processing loops. Const expressions and templates can enable compile time layout optimizations. And stud tuple or structured bindings can help group logic while keeping data separate. Modern C++ gives you powerful tools to write expressive, fast and cache-aware code, if you design with the data in mind. Let's wrap this up with some key takeaways. Data-oriented design is about organizing code around how data is used, not how it's modeled conceptually. The CPU cares deeply about memory layout, especially contiguous access patterns. Separating your data, like moving from array of structures to structure of arrays, can yield big performance improvements. C++ is uniquely suited for DoD because it exposes low-level memory control. You don't need to go full DoD everywhere. Start where it matters. Remember, the goal isn't to abandon clean design. It's to align design with performance realities. Thanks for watching, and if you found this helpful, don't forget to like, subscribe, and check out the rest of the C++ series. Hey everyone, welcome back. Today we are talking about an absolutely essential topic in programming, especially in languages like C++, the heap in memory management. Let's dive straight in. First, let's quickly define what the heap is. In computer science, the heap is a region of a program's memory where dynamic memory allocation takes place. This memory is managed by the operating system and is used when you don't know ahead of time how much memory you will need. In contrast, we also have something called the stack. The stack is fast and automatically manages memory, but it's limited. When you need more flexible, longer-lived memory, you use the heap. In C++, when you allocate memory on the heap, you usually use the new keyword. In this code, we dynamically allocate an integer on the heap. The new keyword asks the operating system for enough memory to hold an integer and returns a pointer to that memory. The important thing to remember is that memory you allocate with new stays allocated until you explicitly free it. If you forget to free it, you create a memory leak. Memory leaks are dangerous because they can make your program consume more and more memory over time, possibly crashing your system. To free heap memory, you use the delete keyword, like this. This releases the memory so that it can be reused. Now, if you allocate an array on the heap, you use a slightly different syntax. Here is an example. This creates an array of 10 integers on the heap. And when you are done with it, you need to free it using delete square brackets instead of just delete. If you forget the square brackets, you might not properly free the entire array, which would cause undefined behavior. Now, you might be wondering, why not just use the stack all the time? The answer is limits. Stack memory is very limited, usually just a few megabytes. Heap memory is much larger, potentially gigabytes, and can handle much bigger dynamic data structures like large arrays, linked lists, trees, and so on. But heap memory is slower to allocate and deallocate because it requires system calls under the hood. Also, you have to manually manage it, which can introduce bugs. In modern C++, we often avoid row new and delete by using smart pointers like std_unique pointer and std_shared pointer, which automatically manage heap memory for us. Here is a simple example with std_unique pointer. When the unique pointer goes out of scope, it automatically deletes the memory it owns. This helps prevent memory leaks. Another thing to keep in mind is fragmentation. As you allocate and deallocate different sized blocks on the heap, it can become fragmented over time. Fragmentation means you have free memory, but it's spread out in little pieces instead of in one big continuous block. This can make it hard to find a big enough block for a large allocation, even though enough memory technically exists. Some systems use heap managers or garbage collectors to help deal with fragmentation and leaks, but in C++ you are responsible for it. Let's quickly review. Heap memory is dynamic. You use new to allocate and delete to deallocate. If you forget delete, you leak memory. Arrays need new square brackets and delete square brackets. Use smart pointers in modern C++ to make life easier. And that's a basic introduction to the heap in memory management. Understanding how the heap works will make you a much better programmer and will help you write faster, safer, and more efficient C++ code. Thanks for watching and see you on the next video. Hey everyone, welcome back to the channel. Today we are diving into a really important concept in systems programming and C++ development. Memory alignment in memory management. Let's break it down step by step. First, what exactly is memory alignment? In simple terms, memory alignment refers to arranging data in memory according to certain boundaries. These boundaries are usually powers of 2, like 2, 4, 8 or even 16 bytes. The goal is to make memory access faster and more efficient for the CPU. You might be wondering, why does alignment even matter? Well, CPUs are optimized to read and write data from memory at specific addresses. If data is not properly aligned, the CPU might have to perform extra work to read it. This can lead to slower performance and even hardware faults on some architectures. Now, let's look at a simple C++ example. Suppose we have this structure. At first glance, you might think this struct takes up 6 bytes. 1 byte for A, 4 bytes for B, and 1 byte for C. But that's not the case. Because of alignment, it usually takes 12 bytes. Let's step through it. Char A is 1 byte, so it starts at address 0. Int B needs to be aligned to a 4 byte boundary, since address 1 is not divisible by 4. The compiler inserts 3 bytes of padding after A to align B at address 4. Then B occupies 4 bytes. Addresses 4 through 7. Char C comes next at address 8. Now, depending on the system, there might be 3 more bytes of padding after C to make the size of the struct a multiple of the largest alignment requirement, which is 4 bytes. You can check the size of this struct by writing this code. This usually outputs 12, so memory alignment isn't just about the variables themselves. It also affects the overall size of data structures. Now, let's talk about how we can control alignment in C++. One way is using the alignS keyword introduced in C++11. For example, this tells the compiler to align aligned example to a 16-byte boundary. This can be very useful for SIMD operations or when working with hardware that requires specific alignments. Another important thing is that improper alignment can cause undefined behavior. On some architectures like ARM, trying to access misaligned memory can cause a crash. When you allocate memory manually, you might need to ensure proper alignment yourself. Before C++17, this was tricky. Now, with C++17, you can use std-aligned alloc. Here is an example. This allocates 64 bytes of memory aligned to a 16-byte boundary. Don't forget, whenever you use aligned alloc, you need to free the memory with free. Now, you might be thinking, can alignment cause fragmentation? Yes, it can, especially if you align a lot of small objects to large boundaries. Memory gets wasted between allocations. This is why memory pools and custom allocators often try to optimize around alignment issues. Let's quickly summarize. Memory alignment improves CPU performance. Misaligned memory can lead to slowdowns or crashes. Compilers automatically add padding to structures to ensure proper alignment. You can control alignment manually using alignS or aligned memory allocation functions. And remember, always check the documentation of your target platform. Different CPUs have different alignment requirements. Alright, that's it for today's video. If you found this helpful, don't forget to like and subscribe for more deep dives into C++ and systems programming. Thanks for watching and I will see you next time. Hey everyone, welcome back. Today we are diving deep into a fundamental part of memory management, how malloc and free work. Even though we are usually coding in C++ on this channel, it's important to understand these C-style functions because they are building blocks underneath the abstractions we use every day. Let's get started by thinking about how memory is organized. When a program runs, memory is typically divided into several segments. There is the stack, the heap, the text segment, and the data segment. The stack is used for static memory allocation, like when you declare variables inside a function. The heap, on the other hand, is where dynamic memory allocation happens, and that's where malloc and free comes in. Now, what does malloc actually do? The function malloc, short for memory allocation, is used to request a block of memory from the heap. The syntax looks like this. Here we are asking the system to give us enough memory to store one integer. Let's think step by step about what happens internally. First, when malloc is called, it checks if there is a block of free memory big enough to satisfy the request. If there is, it reserves that block and marks it as in use, then returns a pointer to the start of it. If there isn't enough memory available, malloc returns a null pointer. Now notice that malloc does not initialize the memory it gives you. The memory could contain any random leftover data. It's purely raw memory. In C++, we usually prefer using new, but behind the scenes, the memory allocation part of new often ends up calling malloc or a similar low-level function provided by the operating system. Okay, but now that we have dynamically allocated memory, we also need to be responsible for freeing it when we are done. That's where free comes in. Let's say we have this code. We can later call this. It tells the system, hey, I'm done with this memory. You can reclaim it for future use. Internally, free takes the pointer you pass it, finds the metadata that malloc stored, usually just before the block you received, and updates its internal bookkeeping to mark that block as free. If you forget to call free, you will cause a memory leak. That means the program holds onto memory it doesn't actually need anymore. Over time, especially in long-running programs, memory leaks can add up and cause the system to slow down or even crash. It's equally important not to double free memory, meaning don't call free on the same pointer twice. That can corrupt the heap structure and cause undefined behavior, which is often very difficult to debug. Here is an example of proper usage. Notice how we check if malloc returned a valid pointer before using it. That's a good habit. Now, there is one more thing. Once you call free, the pointer you had still exists, but it points to memory you no longer own. This is called a dangling pointer. A good practice is to immediately set your pointer to null pointer after freeing it, like this. That way, if you accidentally try to use it later, it will be easier to catch the mistake, because dereferencing a null pointer usually triggers a clear and immediate error. So to summarize, malloc reserves memory on the heap. Free releases it back to the system. Always check if malloc succeeded. Always free exactly once. Set pointers to null pointer after freeing them. Understanding malloc and free is crucial, even in C++, because smart pointers like stud unique pointer and stud shared pointer manage memory safely, but underneath they are built on the same ideas. Alright, that's it for today. I hope you now have a clearer understanding of dynamic memory allocation. Thanks for watching, and I will see you next time. Hey everyone, welcome back. In today's video, we are diving into a key concept in memory management, the stack. If you are programming in C++ or any other language, understanding the stack is essential. So let's walk through it step by step. First off, what exactly is the stack? Well, think of the stack as a special region of memory that your program uses to store data temporarily. It's called a stack because it behaves like a real-life stack of plates. You always add plates on top and you always remove plates from the top. This is known as last in, first out, or LIFO. When you run a C++ program, the operating system gives it a certain amount of memory. Part of that memory is reserved for the stack. It's managed automatically. You don't have to allocate or free memory manually for most stack operations. Let's look at an example. Suppose we have a simple function. When greet is called, two things happen. First, a stack frame is created for this function. A stack frame contains all the function's local variables. In this case, number and message are both stored in the stack frame. As soon as greet finishes running, its stack frame is popped off the stack, and all the memory used by number and message is automatically reclaimed. You don't need to manually delete anything. That's the beauty of the stack. It's fast and self-cleaning. Now let's get a bit deeper. Each time you call a function, a new stack frame is pushed onto the stack. Each frame holds not just local variables, but also information like the return address. Basically, where the program should jump back after the function is done. So, if you have nested function calls like this, when function A calls function B, a stack frame for function B is placed on top of function A's stack frame. When function B finishes, its frame is popped, and control returns to function A. But what happens if the stack gets too big? That's called a stack overflow. It usually happens when you have deep or infinite recursion. For example, every time infinite recursion calls itself, a new stack frame is added. Eventually, you run out of memory and the program crashes with a stack overflow. Now, you might be wondering, what can you put on the stack? Typically small, short-lived data. Primitive types like int, char, float are perfect for the stack. Small structures or simple objects can also go on the stack. But large objects like huge arrays or complex data structures are better placed on the heap, another area of memory, because the stack has limited space. In C++, if you write this, the variable x is stored on the stack. But if you do this, here the pointer p itself is on the stack, but the integer it points to is on the heap. You have to manually delete heap memory to avoid leaks, but stack memory is automatically managed. Finally, why do we care about the stack? Because it's extremely fast. Allocating memory on the stack is basically just moving the stack pointer down, and deallocating is moving it back up. No complicated bookkeeping, no fragmentation. That's why many critical, performance-sensitive parts of programs use stack allocation as much as possible. However, you must be careful. Don't return pointers or references to local stack variables. They will be invalid once the function exits, like this. Here, temp will be destroyed when bad function returns. The pointer you get will point to garbage memory. Always remember, stack memory is temporary. Alright, that's a basic but solid overview of stack in memory management. Thanks for tuning in, and I will see you in the next video. Hey everyone and welcome. Today we are talking about dependency injection in C++. What it is, how to do it, and why it actually matters in real-world code bases. Let's start with the basics. Dependency injection, or DI, is a way to give an object the things it depends on, rather than having it create them itself. That's it. It's a simple idea, but it solves some really important problems in architectures, like tight coupling, hard to test code, and hidden dependencies. Let's look at a small example. Imagine you have a class game that needs a renderer to draw graphics. You might write something like this. Seems fine, right? The problem is, game is tightly coupled to renderer. You can't change the rendering behavior without modifying the game class. You can't substitute a mock renderer for testing, and you are managing memory manually. That's a red flag in modern C++. Now let's refactor this using dependency injection. Instead of creating the renderer inside game, we pass it in from the outside, like this. Now, the game class depends on a renderer, but it doesn't construct it. That responsibility has moved outside. That's dependency injection. So why is this better? First, we can now easily swap out the renderer. Maybe we have a console renderer or a null renderer for testing. And now we can do this. This means game is testable, it's flexible, and you've separated the concerns. Game runs the game, and someone else figures out what kind of rendering to use. Dependency injection supports something called inversion of control. Instead of high-level modules controlling the construction of their dependencies, the control is inverted. The configuration happens outside, often at program startup. That makes your components reusable and decoupled. Now, there are different ways to do dependency injection. What we just did, passing dependencies via
via the constructor is called constructor injection. It's the most common and usually the cleanest. There is also setter injection, where dependencies are passed in through a setter function after construction. Setter injection is useful if you want to change the dependency at runtime, but it comes with the risk that the object is only partially initialized after construction. So use it when that trade-off is worth it. There is also interface injection, where a dependency provides a method to inject itself. This is rare in C++ and mostly used in more dynamic languages. Now let's talk about manual versus framework-based dependency injection. In languages like Java or C#, there are full-blown dependency injection containers that automatically wire up your dependencies. In C++, we rarely need that. Manual dependency injection is usually enough, and it gives you more control over performance and memory. That said, you can write a lightweight factory or service locator in C++ if your project is large enough and you want to manage object lifetimes more dynamically. Let me show you a small example of building a factory function. Now, the creation logic is outside the game class. That keeps your business logic clean and focused. So to recap, dependency injection in C++ means passing an object's dependencies from the outside, instead of constructing them internally. This gives you better testability, lower coupling, clearer object lifetimes, easier to swap or extend components. And all of this adds up to more maintainable code, especially as your project grows. One common anti-pattern you will want to avoid is the hidden dependency. That's when a class depends on something but doesn't say so in its constructor. For example, here, game depends on the logger, but it doesn't say so. That makes the class harder to reason about and harder to test. A better design is to inject the logger, even if it's a singleton. Now, everything game depends on is visible. Alright, that's a wrap on dependency injection in C++. It's not just a buzzword, it's a practical tool that leads to more modular, cleaner and testable code. If you want to see more real-world patterns like this, hit like and subscribe. And please let me know in the comments which C++ pattern you want to see next. Catch you on the flippity flip!
Hey everyone, welcome back. In today's video, we are diving into a very cool feature introduced in C++20, std source location. If you've ever needed to log or track where something happens in your code, like a specific line or function, this feature is going to be super helpful. So what exactly is std source location? At its core, std source location is a utility that allows you to get information about the current source code location. The file name, function name, line number and column number. It's particularly useful for debugging, logging or any kind of diagnostic information where you need to know where something in the code was executed. Let's start by looking at how to use it. Here we have a simple log message function that logs a message along with where it was called from. The std source location current is a specific static member function that captures the current location when the function is invoked. Now let's see it in action. When you run this, the output might look something like this. So instead of hard coding file names or line numbers in your logging code, std source location provides them automatically. But it's not just about logging. It can be extremely helpful for tracing errors, performance diagnostics and other situations where knowing the context of where a function was called is important. A great example is in custom assertions. Imagine you are writing an assert macro. Now, if an assertion fails, you will know exactly where it happened in your code, complete with file name, line number and function name. To recap, std source location is an awesome new tool in C++20 for tracking where code is executed. It can make debugging and logging much easier and cleaner. And because it's so easy to use, it's something you will likely find yourself reaching for in many situations. Thanks for watching. If you enjoyed this video and found it helpful, don't forget to like, share and subscribe.
Catch you on the flippity flip!
Hey everyone, welcome back. Today we are diving into a super important topic in C++ and programming in general. Stack versus heap in memory management. Let's break it down step by step. First, let's talk about the stack. The stack is a region of memory that stores temporary variables created by each function. Think of it like a stack of plates. You can only add or remove a plate from the top. Similarly, in memory, the last variable you created is the first one that gets removed. In C++, when you declare a variable inside a function like this, the variable x is stored on the stack. When my function ends, x is automatically removed from the memory. You don't need to do anything. This is called automatic storage. The stack is super fast because it only has to move a pointer up and down. But there is a catch. The stack is small. If you use too much stack memory, you can get a stack overflow. Now, let's move on to the heap. The heap is a region of memory used for dynamic memory allocation. You manage it manually. If you need a variable to live beyond the scope of a function or you need a large amount of memory, you use the heap. In C++, we use new to allocate memory on the heap. Here, p is a pointer stored on the stack, but the actual integer it points to, the 20, is stored on the heap. Important difference. When you are done with heap memory, you have to free it manually, using delete. If you forget to delete, you have a memory leak, which can cause your program to eat up memory over time. One way to visualize this is, the stack memory is like a stack of plates, where you always remove or add plates at the top. Heap memory is like a big storage room where you can throw stuff anywhere, but you have to remember to clean up after yourself. Now, let's look at a quick comparison. The stack is fast but small. The heap is slower but much larger. The stack memory is automatically managed. The heap memory must be manually managed. Another thing to keep in mind. Accessing heap memory is slower than accessing stack memory, because it involves more steps for the CPU. In real-world C++ code, you try to use the stack as much as possible, because it's efficient. You only reach for the heap when necessary. There are also smart pointers in C++, like std_unique pointer and std_shared pointer. These pointers help manage heap memory automatically. Here is an example. In this case, smart p will automatically delete the memory when it goes out of scope. You don't have to manually call delete. This helps avoid memory leaks and makes your code safer. Another important point. When you pass variables to functions, stack variables are usually passed by value, making a copy unless you use references. Heap allocations are typically passed around using pointers or smart pointers. Quick tip. If your object is small and doesn't need to survive outside the function, use the stack. If it's large or needs to live longer, use the heap. To wrap up, stack memory is like a quick, short-term storage. Heap memory is like a long-term storage, but you are responsible for managing it. Understanding the difference between the stack and the heap will make your C++ code more efficient and bug-free. Alright, that's it for today. If you found this helpful, don't forget to like and subscribe for more C++ content. See you next time. Hey everyone! Today we are going to talk about something that's both simple and powerful in C++, std system. So what exactly is std system? In short, it's a function that lets your C++ program run system commands, just like you would in a terminal or command prompt. It's defined in the cstdlib header, and you can use it like this. That string you pass to std system gets sent to the underlying shell. On Windows, that's usually cmd.exe, and on Unix-like systems, it's typically bin/sh. Let's take a quick example. Suppose you want your program to list all files in the current directory. You could do something like this. When this runs, your program will temporarily pause and run the command. Whatever that command prints to the terminal, you will see in your program's output. So why is std system useful? Well, it can be quick and a dirty way to hook into tools that already exist on the system.
like compiling code, launching other programs, copying files, or even calling Python scripts. It saves time when you don't want to write C++ code to do those things manually. But, and this is a big but, you have to be careful with StudSystem. First, there is a performance hit. Spawning a shell and executing commands can be slow compared to native C++ solutions. Second, it can be dangerous. If you are passing user input directly into StudSystem, you can open yourself up to command injection vulnerabilities. That's where someone could insert malicious shell commands into your input and potentially take control of the system. Also, because it's OS dependent, code using StudSystem isn't always portable. A command that works on Linux might fail completely on Windows, and vice versa. So when should you use StudSystem? Use it when you need something quick and you are sure it's safe and cross-platform compatibility isn't a priority. But for anything serious or security sensitive, look into native alternatives like C++ file system library, StudThread, or process management libraries like boost.process. That's it for now. StudSystem is simple to use, but handle it with care. Thanks for watching, don't forget to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are going to explore one of the most underrated but powerful tools in modern C++, StudStringView. If you have ever passed strings around in your programs and worried about unnecessary copies or performance issues, this video is for you. Let's think step by step and see what StringView does, and why it's such a game changer. So what is StudStringView? It's a non-owning, read-only view of a string. Basically, instead of holding the actual data, it just holds a pointer to a string and its length. This means you can refer to any string-like data, std_string, string literals, character arrays, without copying the contents. Here is a quick example. Now you can call greet with different types. No need to convert everything to StudString or deal with overloads. StringView handles it all. Let's talk performance for a second. Normally, if you pass a StudString by value, it creates a copy. Even passing by const reference means the function expects a StudString. But with StringView, you are passing a tiny, lightweight object, like passing a pair of pointers. Fast and efficient. But here is the catch. Since StringView doesn't own the data, you have to be careful not to use it after original string goes out of scope. So always make sure the underlying string outlives the StringView. Another cool thing, you can do slicing super easily. That's much more convenient than messing with substrings and copies. To sum it all up, StudStringView is a fast, flexible way to work with string data without owning it. It improves performance, reduces copies, and makes APIs more generic. Just remember, it doesn't own the data, so use it wisely. Thanks for watching. If you learned something new today, hit that like button and subscribe for more plus tips. Catch you on the flippity flip! Hey everyone, and welcome back to the channel. In today's video we are going to talk about a super useful but often overlooked feature in modern C++, the noDiscard attribute. If you have ever written a function that returns a value but sometimes forgot to actually use that value, this feature is for you. Let's break it down step by step. So what does noDiscard actually do? In simple terms, it's an attribute that you can apply to a function or even to a type, which tells the compiler, hey, the return value of this function is important, don't ignore it. If you do ignore it, the compiler will give you a warning. Let's look at a basic example. Now, if you call calculate and just discard the result like this, the compiler will warn you because you probably meant to do something with that value. Why is this helpful? Well, it helps catch bugs early. Maybe you are calling a function that returns an error code or a result you need to process. If you forget to use the return value, your program might silently misbehave. Let's take another example using a class. Now, any function that returns error code will also trigger a warning if the result is ignored. That's perfect for things like error handling, where you really want developers to check what went wrong. This feature was introduced in C++ 17 and in C++ 20 it got an upgrade. You can now include a custom message. If someone calls do something and ignores the result, The compiler won't just warn, they will see your message explaining why it matters. Let's think step by step here. You are writing a low-level function. It returns success or failure as a bool. If someone forgets to check that, you might crash later and not know why. By adding no discard, you are putting a safeguard in place. To sum up, no discard helps make your code safer and your intentions clearer. It tells users, don't ignore this, it's important. Simple, effective, and a great habit to get into. Thanks for watching, and if you found this helpful, be sure to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video, we are diving into one of the coolest and most flexible types introduced in C++ 17, std variant. Let's think step by step. Imagine you want to store either an int, a float, or a std string in the same variable. In older C++, this usually meant reaching for pointers, unions, or writing some custom class. But now with std variant, it's clean, type safe, and way easier to manage. So what is a variant? At its core, std variant is a type safe union. It can hold one of several types, and the compiler keeps track of which type it currently holds. Think of it like a box that can hold either an int, a float, or a std string, but only one at a time. Here is a basic example. In this line, data can hold an int, a float, or a std string. Let's set a value. Each time, the type inside data changes. But how do we read the value? You can use std_get to access the value. But here is the catch. If you try to get the wrong type, it throws std_bad variant access. So it's best to check what's inside first, using std holds alternative. Or even better, use std_visit. This will call the lambda with whatever type is currently held. It's clean, modern, and works with all types in the variant. Let's consider a use case. Imagine you are building a config system, and the setting might be an int, a float, or a string. A variant handles that perfectly, without complex inheritance or custom wrappers. To summarize, std variant brings flexibility while staying type safe. It's perfect for modeling data that can be one of many types, and it pairs beautifully with std_visit for clean access. That's it for today's video. If you found this useful, hit like, subscribe, and let me know in the comments what feature you want to see next. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into the world of STL containers, and specifically we are going to explore std unordered multiset. So what exactly is an unordered multiset? Let's think step by step. You might already be familiar with std set or even std unordered set. These are containers that store unique elements, meaning no duplicates allowed. But sometimes you do want to store duplicates. And you also don't care about the order of elements. That's exactly where std unordered multiset comes in. It's part of the unordered set header, and just like the name says, it's unordered, meaning it does not maintain any specific order. And it's a multiset, which means it allows duplicates. Let's look at a basic example. This code will output values, but not necessarily in the order you inserted them. That's because it uses a hash table under the hood, not a sorted structure like std set. So why would you use unordered multiset? The big reason is performance. Since it's based on hashing, insertions, deletions, and lookups, all take constant time on average, O1. That's a big win if you are working with large datasets and don't need sorting. Another great feature is the duplicate support. Let's say you are counting how many times values appear, or storing items where duplicates are valid, like quotes or word occurrences. Unlike unordered set, this container won't silently discard your duplicates. Here is another example. Now nums will contain free 2's, because duplicates are perfectly allowed. You can also use functions like count to check how many times a value appears. So to recap, std unordered multiset is your go-to container when you want fast access using hashing, you need to store duplicate values, and you don't care about the order. That's it for today's breakdown. If you want to dig into the differences between this and other sets like stud set or stud multiset, let me know in the comments. Thanks for watching, don't forget to like, subscribe, and catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video, we are diving into stud tuple, one of the most flexible and underrated tools in the C++ standard library. Let's think step by step. Imagine you want to return multiple values from a function, like an int, a string, and maybe a float. Normally, you would have to define a struct or pass variables by reference, but with stud tuple, you can group multiple values of different types into a single object super easily. Here is a quick example. Just like that, you've created a single variable that holds an int, a string, and a float. No need for a custom type. So how do you access the value inside? The studget function uses a zero-based index to pull out the element you want. Easy and clean. Now, here is where it gets even cooler. Let's say you want to return multiple values from a function. You can return a tuple directly. And on the receiving side, you can unpack the tuple like this. That's called structured bindings, introduced in C++ 17. It makes working with tuples so much nicer and more readable. But that's not all. Stud tuple also supports comparison, concatenation with stud tuple cat, and even compile time introspection using stud tuple size and stud tuple element. Here is one more handy use case. Imagine you are dealing with function parameters of different types and want to store them together. You can just pack them into a tuple and pass that around. Also keep in mind, if you don't like typing out the full type name, you can use auto or stud make tuple. C++ 20 also gives us tuple swap and better constexp support, making tuples even more powerful. So to wrap it up, stud tuple is your go-to tool when you need to group multiple values of different types into one container, especially for returning multiple values cleanly from functions. If you found this helpful, make sure to like, subscribe, and hit the bell for more C++ tips. Thanks for watching, catch you on the flippity flip! Hey everyone, welcome back. In today's video we are going to talk about studany, a powerful and flexible utility introduced in C++ 17 that lets you store any type of value in a type-safe way. Let's think step by step about what this actually means. Normally in C++, when you declare a variable, the type is fixed. An int can only store integers, a stud string holds strings, and so on. But what if you want to write a function or class that can hold anything, without knowing the type ahead of time? That's exactly what studany is for. At its core, studany is a type-safe container for single values of any type. It works a bit like a box. You can put anything in the box, but you need to know what's inside before taking it out. Here is a basic example. In this code we assign an int to a studany variable. To get the value back, we use studanyCast with the correct type. If you cast to the wrong type, it throws a bad anycast exception. Now here is something cool. You can assign any type. For example, so why would you want this? Let's say you are building a plugin system, a scripting interface, or even a UI where values can be of different types. Int, float, string, and so on. Instead of writing a separate logic for each type, you can use studany to store them in a uniform container, like a stud vector containing studany types. But here is the catch. Because it's type erased, you lose compile time type safety. You have to manually cast it back, and if you get the type wrong, it will either throw or fail silently, depending on how you check it. So use it wisely. It's not a tool you want to use everywhere. But when flexibility is more important than strict typing, studany can be a lifesaver. To check the type safely, you can use value.type.name for debugging or use studanyCast to return a pointer that's null if the type doesn't match. Alright, that's a quick intro to Studeni. It's a clean and powerful way to work with dynamic types while still playing within the bounds of modern C++. Hope this helped. If it did, hit that like button. Catch you on the flippity flip!
Hey everyone, welcome back to the channel. Today we are diving into something that's both super efficient and kind of underrated in C++. Stud bitset. If you've ever needed to work with binary data, flags, or just want a memory efficient way to store bits, then bitset is your new best friend. Let's start simple. What is a bitset? In C++, stud bitset is a fixed size container that stores bits, ones and zeros. Unlike integers, which also use bits under the hood, bitset gives you direct control over each individual bit. You can set them, reset them, flip them, and even test their values, all with a clean and easy to use interface. Let's think step by step. Say you want to represent 8 bits. You can create a bitset like this. Now you have 8 bits, all initialized to 0. Want to set the 3rd bit? Want to flip all bits? Want to reset everything to 0? You can also access bits just like an array. And here is a really nice feature. You can construct a bitset from a string or an integer. So why would you use bitset instead of something like int? Well, with bitset you get bit level control and built-in methods that make code easier to read and maintain. You can even count how many bits are set, or check if none are set. Another cool trick, you can perform bitwise operations directly. To sum it up, stud bitset is perfect when you want to work with a known, fixed number of bits efficiently, with clean syntax and full control. That's it for this video. I hope you learned something new. If you did, drop a like, maybe subscribe.
Catch you on the flippity flip!
Hey everyone, welcome back. In today's video we are diving into a super convenient feature introduced in C++20, stud format. If you've ever struggled with formatting strings in C++ using stud cout, printf, or string streams, this one is for you. Let's start with the problem. Traditionally, formatting in C++ wasn't exactly elegant. You either had to use stud string stream, which is clunky, or the old printf style functions, which are type unsafe and prone to bugs. Wouldn't it be nice to format strings cleanly and safely like in Python? Well, with C++20 you can with stud format. Here is a simple example. Just like that, hello world gets printed. No need to mess around with streams or worry about types not matching format specifiers. Let's think step by step about what's going on here. Stud format takes a format string and any number of arguments. Inside the format string, you use curly braces as placeholders. Each curly brace is replaced by the corresponding argument in order. It's clean, it's readable, and it's safe at compile time. Now, what if you want to include formatting options? You can easily do it like this. Here, less than 10 left aligns the first value in a field of width 10, and greater than right aligns the second value in a field of width 5. This gives you tight control over output layout, perfect for building tables or logs. And the best part, it works with user-defined types too, as long as you implement a formatter. That gives you complete flexibility. You can even format numbers like this. This prints the number in hexadecimal with the 0x prefix. No manual conversion required. So why should you use stud format? Well, it's modern, safe, type-checked at compile time, and incredibly clean. It's part of the format header, and it's here to replace many of the old, clunky formatting techniques we've dealt with for decades. To wrap up, if you are using C++20 or later, stud format is an absolute game changer. It makes your code cleaner, safer, and more professional. That's it for today's video. Don't forget to like and subscribe.
Catch you on the flippity flip!
Hey everyone, welcome back.
In today's video, we are diving into something a little underrated but very useful: stud placeholders. You've probably seen them used with studbind, but maybe you weren't quite sure what was going on. So let's break it all down, step by step. Alright, so what are stud placeholders? In simple terms, they are part of the functional header and are used with studbind to create function wrappers. Kind of like pre-configured versions of functions where some of the arguments are already fixed and others are left to be filled in later. Let's take a simple example. Suppose you have this function. Now let's say you want to create a version of add where the first argument is always 10. That's where studbind and stud placeholders come in. What this line does is create a new function object called add10, where the first parameter to add is fixed to 10 and the second is still open. Stud placeholders 1 means the first argument you pass to the new function. So now you've effectively delayed part of the function call. This is really useful when you need to adapt functions to fit into different APIs, especially ones that expect callbacks or function pointers with a specific signature. Let's think step by step about a real-world use case. Imagine you are working with a GUI library or some kind of event system that expects a function with just one argument, like a callback that takes a button ID. But your logic needs more context. You can use studbind with placeholders to sneak in extra arguments and still satisfy the expected signature. You can chain multiple placeholders too. Now it swaps the two arguments. Kind of cool, right? One thing to note. While studbind and stud placeholders are powerful in modern C++, lambdas are usually the preferred way to do similar things. But for legacy code or quick adoptions, studbind still has its place. That's it for today. Now you know what stud placeholders are and how to use them with studbind to build flexible, partial function calls. If this helped clear things up, give it a like and subscribe for more C++ tips. Catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video we are diving into one of the most essential tools for modern C++ developers, stud unique pointer. So what exactly is unique pointer? Let's think step by step. In C++ we often deal with dynamically allocated memory using new and delete, but managing memory manually can lead to bugs, especially memory leaks or double deletes. That's where smart pointers come in. And stud unique pointer is the simplest and safest of them all. A unique pointer is a smart pointer that owns a resource, and only one unique pointer can own that resource at a time. When the unique pointer goes out of scope, it automatically deletes the resource it owns. You don't need to call delete, it's all taken care of. Here is a quick example. We just created a dynamically allocated integer with the value 42, but there is no new keyword here. Make unique handles that for us. And better yet, we never need to call delete. Now, why is it called unique? Because it can't be copied. Only one unique pointer can own the object at any time. If you try to copy it, the compiler will throw an error. But you can move it. After this line, pointer no longer owns the resource. Pointer 2 does. This transfer of ownership is what makes unique pointer so safe. It enforces a strict ownership model. Let's look at a class example. This is clean and safe. If an exception is thrown later, you don't have to worry about leaking memory. Unique pointer will handle the cleanup automatically. Now here is a tip. Always prefer stud make unique over using new. It's safer, shorter and exception friendly. To summarize, stud unique pointer owns a resource exclusively. It deletes the resource when it goes out of scope. You can't copy it, but you can move it. It's perfect for managing memory automatically and safely. That's it for today's video. Unique pointer is an absolute must-know for modern C++ programming. If you found this helpful, don't forget to like and subscribe. And let me know what C++ topic you want to see next. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into one of the coolest additions from C++ 20, StudSpan. Now, if you've ever passed around row pointers and array sizes in your code, you know it can be error prone and kind of messy. StudSpan is here to clean that up.
It gives you a lightweight, bounce-safe view over a sequence of elements, like an array or a vector, without actually owning the data. Let's break it down step by step. So what exactly is StutzSpan? Think of it like a window or a view into an existing array or container. It doesn't copy anything, it just wraps the data and gives you safe, easy access to it. Here is a simple example. Now you can call this function with a vector, an array, or even a C-style array. See how clean that is? No need to pass a pointer and the size separately. And bonus, StutzSpan knows its size, so it avoids out-of-bounds access. That's a huge win for safety. Let's think about a typical use case. Before StutzSpan, you might have written a function like, then you would have to manually make sure that the pointer isn't null, the size is correct, and you don't read off the end. With StutzSpan, all of that gets wrapped into a tidy, expressive package. A span can also refer to just part of a container. It even works with multi-dimensional spans, though that's a bit more advanced. Now keep in mind, StutzSpan doesn't own the data, so make sure whatever it's pointing to outlives the span itself. If the data goes out of scope, you are in trouble. To wrap it up, StutzSpan is an elegant, zero-overhead way to work with continuous ranges of elements. It makes your function safer, cleaner, and more flexible, all without sacrificing performance. That's it for this one. If you like this breakdown, give it a thumbs up and subscribe for more modern C++ content. Catch you on the flippity flip! Hello everyone and welcome to today's video, where we break down one of the exciting new features introduced in C++20, the spaceship operator, represented by this symbol. In this video I'll explain what this operator does, how it simplifies comparisons, and why it can be a game changer in writing cleaner and more maintainable code. Let's start with a bit of background. The spaceship operator is also known as the three-way comparison operator. Traditional C++ comparisons using operators like less than, greater than, and so on often lead to verbose code when implementing sorting algorithms, or even basic object comparisons. With the spaceship operator, the language provides a unified way to compare values. It's designed to return a value that clearly indicates whether the left-hand side is less than, equal to, or greater than the right-hand side. When you write an expression like this, the operator evaluates the relationship between the two operands and returns an ordering result. This result is typically one of several types of ordering categories, provided by the standard library, such as std-strong ordering, std-weak ordering, or std-partial ordering. Each category informs the user of the precise nature of the comparison. For instance, if the operands are completely ordered with no ambiguity, std-strong ordering is returned. Let's think step by step about how this works. Imagine you have two integers. In this case, since 5 is less than 10, the spaceship operator returns a value that indicates the relationship. This single operator replaces several lines of code that you might have otherwise written, like checking for equality first and then comparing which is greater or less. This reduction in verbosity not only makes your code cleaner, but also minimizes the potential for errors. Moreover, the spaceship operator enables the compiler to automatically generate default comparison operators for your user-defined types. By simply marking your class with the appropriate defaulting, you allow the compiler to deduce the proper behavior based on your members. Consider a simple class example. In this example, the operator first compares the x coordinates. If those are equal, then it moves on to comparing the y coordinates. This built-in logic streamlines the process of ordering objects. It's intuitive and saves valuable development time. That's it for today's video. I hope you now have a clearer understanding of how the spaceship operator works in C++ and why it's such an important addition to the language. Catch you on the flippity flip!